concerned, we have to pay attention to. We have the dehydration of alcohols. We have the dehydrohalogenation of alkyl halides. And then we have the dehalogenation of vicinal dihalides. Example, debromination. At this stage, my advice is for you to pay critical attention to something. For every reaction, whether in the synthesis or reactions of organic molecules, there is always the starting material. There is always the starting material. There is always the reaction conditions or reagents that have to work on the starting material and convert the starting material to an expected product. And so there is always the product aspect. So whenever we talk about reactions, there's something you are starting with. There's something or a condition or an atmosphere that you have to provide for that particular starting material to be transformed into what you expect, which we call the product. So usually when you write a chemical equation, at the left side of the equation, we call that one the reactant, the reacting species. Then there is an arrow which implies to form. Whenever you see an arrow, it implies to form. And on that arrow, we normally will put the conditions or the reagent that is needed for that particular reaction to take place or to convert the starting material to the expected product. Then on the right side of the equation is the product formed. So here we're going to take you through a number of reactions, and you need to pay attention to the starting material for each of the reaction, pay attention to the specific condition or reagent for each of the reaction, and then have in mind the expected product such reactions are to produce. So we are looking at the first type of the elimination reaction, dehydration of alcohols. Now, dehydration of alcohols, it means that we need an alcohol, and an alcohol is an organic compound with a hydroxyl functional group bonded to an sp3 hybridized carbon. An example of an alcohol is ethanol, methanol, propanol, butanol, and so on and so forth. Now, the word dehydration, D means to remove. What are you removing? You are removing water. So dehydration simply means removal of what? Water. So for this one, if you have an alcohol and you remove water from it, you form an alkene. So in the dehydration of alcohols, the reaction is indeed catalyzed by an acid. So here, the acid catalysts serve as what? The reagent. And of course, the reaction also requires some level of what? Temperature, depending on the nature of what? The alcohol. Alcohols are classified into primary, secondary, and tertiary. The primary alcohols are very difficult to dehydrate. So then over there, the concentration of the acid should be high. That's the catalyst. Again, the temperature under which the reaction is being performed also should be very high before a primary alcohol can easily be dehydrated. The tertiary alcohols, they are easily or readily dehydrated. So even at the least or at the lowest temperature, they easily get dehydrated to form an alkene. So on the screen, you can see an alcohol. It's an alcohol because you have an OH bonded to an sp3 hybridized carbon. Now, what you see here is a generalized representation of an acid. We didn't represent the acid with any known one. So the HA is just telling you that it could be any acid. It could be ACL, it could be HBr, it could be HI. Okay, it could be any acid. Then heat. Then heat. And then you form your alkene. And because in the formation of the alkene, you are removing water, you form water as a byproduct. So the principal product is the alkene, and then the byproduct is water. Now, this is an alkene because of the double bond. So the introduction of the double bond is always between the carbon that the alcohol functional group is bonded to and an adjacent carbon and an adjacent what? Carbon. So between these two carbons, you bring your double bond. The carbon that the OH is bonded to, and then an adjacent carbon, you introduce your double bond. But before you introduce your double bond, the OH will be removed with what? An adjacent hydrogen, which will form the water, and then they'll go away. So they don't appear again in the final product. So this hydrogen and the OH together is what is forming the water. Then you introduce the double bond between the two carbons where those two components were removed. So anytime you are giving an alcohol and then under an acid catalyzed condition and heat, and you are asked to form an alkene product, know that the double bond will be formed between the carbon where the OH is attached and the adjacent carbon where you remove the hydrogen. So there's another typical example. See, the OH is here and the hydrogen is here. This is ethanol. So if you remove water by taking away this hydrogen and the OH, then the double bond comes there and you form your alkene and water. Like I indicated,
we can't see your screen.
you cannot see my screen.
It's now appearing. Thank you.
All right.
Hello, sir.
Yes.
Please, previously you said when it is forming, the H and then the OH forms the water and it will not come in the final product again. But what
Yes.
is displayed on the screen right now, I can see the HH there.
Okay. So you
That's
see, have you seen this carbon that Mankesa is pointing to?
yes, sir.
Okay. So that carbon, carbon is tetravalent. It should always form 4 bonds. So it is bonded to
Okay.
this carbon singly. And then
Okay.
it has what? 2 hydrogens on it, and then the OH. Okay. So if you remove this OH, you are left with what? These 2 hydrogens on it, and they are there.
Okay.
Now, if you
Understood.
consider this adjacent carbon here, there are 3 hydrogens, but not all the 3
Okay.
hydrogens are going to be removed. Only one of them will go. When
Okay.
one
Thank
of
you.
them goes, you have 2 more hydrogens left, just to maintain the
Okay.
tetravalent nature of carbon.
Okay. Thank you.
So these are all examples. But then earlier on, I was just indicating that primary alcohols are difficult to dehydrate. And for that matter, you expect that the temperature under which you are performing your dehydration should be high, as well as the concentration of the acid catalyst. But tertiary alcohol, like the one you see on the screen, pet butyl alcohol, we are not doing alcohols at this level. In your semester 2, I'll be back teaching you organic chemistry 2, where we'll start with the alcohols, and I will give you more information about the classification of alcohols and what have you. But what you see here is a tertiary alcohol. And so the tertiary alcohols, you see that the OH is bonded to a tertiary carbon. Of course, you know what a tertiary carbon is, a primary carbon is, a secondary carbon. So for tertiary alcohol like this, you realize that at the least temperature and concentration of the acid, the dehydration takes place and you form your alkene. Now, this is that for the first reaction. So we should have gone to the second reaction, but then for the purposes of maybe detailed understanding, I have to take you through the mechanism for the dehydration of alcohols at this point. Now, when we say the mechanism, what is it? The mechanism is then going to tell you the step-by-step detailed processes that the reaction we just talked about go through. So I've just told you that, when you have an alcohol and the acid catalyst at a temperature, you remove water, you form an alkene. And that the alkene that you are forming, the carbons, the two carbons that is bearing the OH and then the hydrogen, when you remove the OH and then the hydrogen, you bring a double bond there. This looks very simple, very simple. Simplicity. But the mechanism then tells you the step-by-step detailed processes that particular reaction will have to go through before you form the alkene. And that will also help you to appreciate what is happening. So now let's look at the mechanism. Of course, in an exams, I will not ask you to show the mechanism, okay? But I'm just giving this because some of you will be majoring in chemistry. So for the sake of our chemistry major students, they will need these things the more as we move on with the program. So there are 3 steps. There are 3 steps involved in the mechanism. The first step is that the alcohol that has to be forming the alkene get protonated. The alcohol gets what? Protonated. Now, when we say protonation of an alcohol, it means that the alcohol accepts a proton from an acid. The alcohol accepts a proton from an acid. So if you look here, this is our alcohol. Now the OH, the oxygen, of course, has 2 lone pair of electrons. So that makes the alcohol what? Nucleophilic. Now I'm making use of the choice of words, and I know when I mention that you know what it means. So the alcohol is what? Nucleophilic. It's a nucleophile. It's electron rich. Now the acid, the H plus in the acid is also what? Electrophilic, electron deficient. So you expect that anytime that there's a nucleophile and an electrophile, then there will be a reaction. So the nucleophile is going to attack the electrophile. Usually, the arrow always move from the negatively charged species, which is the nucleophile, to the positively charged species, which is the electrophile. So that's how you can see. So the alcohol picks on this hydrogen onto the oxygen. Now, oxygen is divalent. Oxygen should form what? 2 bonds, always. Oxygen should always form 2 bonds, always. So if oxygen picks on this hydrogen and add it to itself, as you can see here, I hope you can see my arrow, my cursor.
Yes, sir.
Good.
Yes,
Now, the oxygen at this point is having how many bonds? 3, which is unusual. So oxygen assuming 3 bonds, then assume a positive charge on it. And so that's why you see a positive charge on oxygen. And that is what we call the protonated alcohol. The protonated alcohol. Now, this protonated alcohol is very, very, very unstable. Very, very unstable. Why is it unstable? It's unstable because of the positive charge on the oxygen. So it makes the whole molecule what? Not stable. And in chemistry, when the molecule is not stable, usually it will not exist. It will cease to exist. It will either cease to exist or arrange itself to forming something else that is stable. So the protonated alcohol is very, very unstable. So at this stage, to get to a more stable form, something has to happen. And that is the step 2. Sorry. That is the step 2. Now, at the step 2, the protonated alcohol then loses a molecule of water. That's why we say the reaction is what? Dehydration. You are removing water. So the protonated alcohol loses a molecule of water to become a carbocation. A carbocation. Jadine, you said it's not easy. What is not easy? Please, I'll get back to you. If you have a challenge, let me know. Jadine, that's why I'm here. If you have any challenge, let me know. I'm sure you all have chemistry background. Now you see the first 2 weeks I told that they were just preliminary. We have not started the organic. We are now starting the organic proper. Okay, so this and then next week is organic proper. Yes, Abubakar Idris, your hand is up.
Please, I would say I appreciate the way you are delivering the lecture, and I wanted to know if you will be the same person who will set the exam for the entire chemistry program at that week.
Abubakar, why do you want to know? That this is not chemistry question. I told you were going to ask me a chemistry question. Your question is not chemistry question, and it has nothing to do with dehydration of alcohol. So please ask a question on dehydration of alcohol.
The reason being is that it's like me per se, I've been following your lectures, but not into this group. I'm affiliated to the UCC platform, but normally follow yours.
Your center is UCC. Your center is UCC. Your center is UCC.
Yes, please.
So you have no business to be on this particular lecture platform. Your lecture is ongoing with Gladys Hayford. So you should join that one. If not, consistency. You see, my class is solely online. They don't have the opportunity to do face-to-face, okay? But I have appointed a tutor for UCC Center, and then I have appointed another tutor for Wesco. Is that right? So the Wesco man is teaching, as we are also having hours. The UCC woman is also teaching, as we are having hours. Okay. So please, if you crisscross, it will not help you. If you crisscross, it will not help you. Make sure you stick to your group, and then you will be okay. This particular group is totally online, which me as the chief examiner or the coordinator, I'm supposed to handle them. All right. They are at a disadvantage because they wouldn't have the opportunity to have face-to-face, and so solely online. And I'm doing my best to make sure that they also will finish. I hope you are okay.
Yeah, very much.
All right. Somebody, Paulina, can you mute yourself? Paulina, please mute yourself. Good. All right. So I didn't want to answer Idrisu because I didn't know why he was asking whether. Yeah, definitely. I'm the coordinator and the chief examiner for this course. So if you have any challenge, let me know. Okay. Even if your center, you have any challenge, let me know. And then I'll address it for you. All right. Let's move on. So the second step is where we are saying the protonated alcohol. And please remember, my questions always comes out the way I lecture. So if you're always at my lectures, I always stress on some very important points. So if you pay attention, you always will get an A in my course. So pay attention. And now you all know what a protonated alcohol is. And we know that protonated alcohols are very, very unstable. And I've explained why they are unstable. So now the protonated alcohol loses a molecule of water to become a carbocation. In other words, a carbonium ion. Wherever you see a carbocation is the same as carbonium ion. And that second step is the slowest step. And normally the slowest step in any reaction is the rate determining step. Meaning the rate of formation of your final product is dependent on that particular step, the slowest step. The first step is very, very fast, and that is the protonation. Hello?
So we are here.
Okay,
yeah.
I thought,
We can hear you.
all right, I thought my internet dropped. Okay, so that is the second step, the formation of what? The carbocation. Now, please, somebody will ask, what is a carbocation? If you look on the screen, okay, you could see that there's a positive charge on the carbon where the water was. Okay, so where, let me just use my cursor. You see the portion labeled with red. Okay, when you have oxygen with two hydrogens, that means that portion can break off as water. So that oxygen carbon bond will then break off so that you have this whole portion being removed as what? Water. Now, when that portion breaks and you have this intermediate, you can see that the first carbon here, the first carbon, how many bonds? You can see it's having 1, 2, 3, 4 bonds. But then the second carbon here is having what? 1, 2, 3 bonds. Carbon is tetravalent. It should always have 4 bonds. Now, where it is having 3 bonds, it means that that is not possible. And that is where the carbon will assume the positive charge. Okay. And when there's a positive charge on carbon, we refer to as what? A carbocation or a carbonium ion. And it is this intermediate carbocation that is finally going to form the alkene. It is this intermediate carbocation that is going to form your final product alkene. So you move to the third step. Now, at the third step, the carbocation that we produce at the second step loses a proton to a base and forms the double bond, meaning a base will come in and then the hydrogens that are on the adjacent carbon which are acidic, the base will pick on one of them. And when the base pick on that hydrogen, that bond between the carbon and the hydrogen, that bond will break onto the single bond and form your double bond. So initially, between the two carbons is a single bond. Now, you are picking this adjacent hydrogen by a base. So its bond here must break onto the single bond here to form the double bond. As soon as you form the double bond here, come to this side. The two carbons now all have 4 bonds. Because the double bond is 2, and then the other 2 bonds here make this one having 4, and then this one to having 4. And that is your alkene product. So this mechanism, like I said, I will not ask you in an exams, okay, to show the mechanism involved in the dehydration of an alcohol forming an alkene. For the chemistry majors, yes, it will get your point. I'll ask them because they will do a question, they will do a course under organic reaction mechanism, solely a course in that area. And when we get to that point, I'll be asking them such questions. But for you who are doing introduction to organic chemistry and you need something small to top up something, I will not disturb you with the mechanism. But then I'm just explaining to you for you to appreciate that particular reaction we just look at, so that it will not look like something abstract. Okay, good. All right. Stability of carbocations. I've mentioned carbocation, and we say that it is the intermediate product that is formed in the alkene formation from an alcohol. Now, let me make a statement here so that you can also appreciate what we are talking about. In chemistry, if you are forming a product and that product is not stable, either a little of that product will be formed or it will not be formed at all. I take it again. In chemistry, if you are forming a product and that product that you are forming, that compound that you are forming, that molecule that you are forming as a product, it is not stable, then very little of that product will be formed, or the product will not be formed at all. Meaning, if the product is stable, then that product will be formed more or in good yield. But then the stability of a product is dependent on the intermediate product. So you see the mechanism I took you through. We didn't form the alkene straight away. From the protonation of the alcohol, we formed a carbocation at the second step, which is the intermediate product. And it is the carbocation which gave us the alkene. So before the final product, there's an intermediate product. Now, if the intermediate product is stable, then automatically the final product will be stable. If the intermediate product is not stable, then the final product will also not be stable. And so because we are forming alkene from an intermediate carbocation, then we need to know the stability of what? Carbocation. So that if an alkene is formed from a particular carbocation, you can tell whether that alkene will be stable or not stable. So what you see on the screen is the trend, which talks about how stable the carbocation types are. And the most stable one, if you look at the arrow trend, is the tertiary carbocation. You know, so please, when you see this is not 3 degrees, okay? In chemistry, when you see 3 with this superscript, you know, it is not 3 degrees, it's tertiary. So this one is what? Secondary. And this one is what? Primary. Okay. So with our previous knowledge in the classification of carbon, which that one I took you through the first week, that A primary carbon is a carbon that is bonded to only one carbon. A secondary carbon is a carbon that is bonded to 2 other carbons. A tertiary carbon is a carbon that is bonded to 3 other carbons. So whenever there is a plus, a positive charge on a carbon that is bonded to 3 different carbons, then that particular carbocation is said to be what? A tertiary carbocation. When there is a carbocation form, a positive charge on a carbon, and that carbon is bonded to 2 other carbons, that carbon is a secondary carbon, then the carbocation is what? A secondary carbocation, and so on and so forth. So this one is a primary. And then this one, you see that the carbon here is not bonded to any other carbon. So it's what? Meta carbocation. So meta carbocation is the least stable, followed by primary, secondary, and tertiary is the most stable. Yes, in an exams, I'll ask a question here. And the question will look like, I will give you about 3 or 4 carbocations, and I'll ask you to arrange them in order of what? Increasing stability. So you should be able to identify a tertiary carbocation, you should be able to identify a secondary and a primary and maybe a meta. Then, based on that, you can then arrange them, knowing very well that the tertiary is the most stable, followed by the secondary, and then the primary in that order. So you can even pick some of my questions last year, and you see that there's a question on this stability of carbocation, the trend. Yes, there's a hand up, Edward. Yes, please.
Sir, good morning.
Good morning.
I'm pleading if maybe by the end of the lecture you can give us some of the sample questions. This is just a plea.
Oh, have I not given you? I thought I've given.
I've given
tutorial questions, right?
Yes, please.
Okay, so tell your course reps they are to do a good job for you. I'm a very busy person, but then if they continue to disturb me the more, they will get every information that you need. Usually I give what I call review questions, apart from tutorial questions. And the tutorial questions, you are supposed to be trying your hands on them based on the materials I will give you, based on the lectures we'll have, be answering them. It's very, very important. And then I'll also be giving you review questions. Now, the review questions, some of them, or most of them, I have provided an answer to guide you. It doesn't mean that go and learn the answer, but then whilst you are answering the questions, then you compare your answer to the answer I've provided to see whether you are on the right path. So I do give all this. I thought I have given I know I've given some. Yeah.
Questions.
Okay, I've given some, but then there's more I'll be giving. Yes, it's that's my responsibility, and it's part of the structure of the course. That's I'm supposed to make lecture slides available to you, make tutorial review questions, materials that will help you to on your own. Because please, the course content is a lot. It's not everything that I'll be able to touch on here. And so you'll be doing a lot of the learning yourself, and you need those materials as a guide. So please, the course reps do remind me. You have my number. Just be sending me WhatsApp and then I'll be doing justice to it. Yes, there's a last hand up. Let me take it before I continue. Zadagli.
Good morning, sir.
Morning.
Please, I just want to be sure of something. Did you say the tertiary carbocation are the most stable ones?
Yes, please. Yes, please.
All right. Thank you.
Followed by the secondary, the primary, and then the meta carbocation is the least stable. Okay. And how to identify them is very key, because what you see on the slide in real exams, I give very specific examples, okay, with some being primary, some being secondary, some being tertiary. And then I'll ask you to arrange them in order of what? Increasing stability. Okay.
Okay.
And so if you can't identify a tertiary carbocation, how then do you arrange it? If you can't identify a secondary carbocation, how do you arrange it? So I've told you that when the positive charge is on a primary carbon, it's a primary carbocation. When the positive charge is on a secondary carbon, it's a secondary carbocation, and so on and so forth. And we already know what a primary carbon, secondary carbon, and tertiary carbons are. Yeah, so tertiary alcohols, in the dehydration of hey, you want to ask plenty of questions, then we will not finish you. All right, Joshua.
Sir, please, good morning.
Morning.
Sir, please, I need some small explanation on carbon ions.
Explanation.
Carbon ion. No, carbon ion.
Okay, so those who be doing further chemistry courses, that is the organic reaction mechanism I told you about, the chemistry major. They will get your point. They will get to know that we have carbanions, we have carbons, we have carbocations. These are all intermediate species depending on what is happening. When you have a positively charged or a positive charge on a carbon, it's a carbocation. Then when you have let's say an electron on a carbon, it's a radical. Okay, then when you have a negatively charged on carbon, it's a carbanion. Okay, so at this stage, I've introduced you to carbocation, so no only carbocation for now. Okay, in the course of the class, I mean, you semester 2 too, you'll be doing some organic, and the other ones will be coming in there. Now, not to get confused. Yes. Any other question?
Yes, sir. Doc.
Yes, please go ahead. Yeah, Isaac, go ahead.
Good morning, Doc.
Good morning.
Please, beginning of the course, you told us we'll be getting the slides and then the recordings. But Doc,
yes,
after
please.
now, the recordings, we have not seen some on the platform. I don't know how we are going to.
All your lectures are recorded by the e-learning units of the college, and I think they have been sharing on your page. The link. Please, if you when you
go to YouTube, get everything.
Yeah,
okay,
when you go to YouTube, so please link up with your colleagues and let them guide you. Okay, this lecture that is ongoing is being recorded, and they are all available. So even later, some of the things that I will touch on here and you are not able to capture it, you can go back and watch the video and then you get it. Okay.
Okay. Thank you, Doc.
Welcome.
Okay, Doc. Please, I want to ask a question.
Please ask.
Yeah, so in this case, what we are doing currently, we should be concentrated on the stability and the increasing order of ions.
Carbocations. Which
carbocations.
So if you just look at the screen, the slide that is showing, so here you can see that there's a meter carbocation there, there's ether, then there's isopropyl, and then there's the tet butyl cation. Now, what is happening is that the trend is that the tertiary is the most stable, as I've explained. Now, let me talk about even the rationale behind that stability trend. What makes the tertiary more stable is that having a positive charge on carbon, okay, because the carbon should have 4 bonds. Now it's having 3 bonds. That's why it's having a positive charge. Now, when there's any charge on a carbon, it makes the molecule unstable. Okay. In the case of the tertiary, okay, you have 3 methyl groups. Okay, and methyl groups are electron donating groups. So they are pushing electrons to the positive charge to neutralize it. And when the positive charge is being minimal, okay, it's being neutralized, it makes the molecule more stable. Here, you have 3 metal groups donating electrons to stabilize or neutralize the positive charge. Here, you have 2 metal groups. Here, you have only 1. Here, there is no metal group to donate electrons to stabilize it. Okay, so in real situation, let me say that when you have a situation to save, you want to save somebody, and it requires strength, and there may be one person is trying to pull somebody by way of saving, and then the person gets a helping hand, 2 people are pulling, the person gets extra hand, 3 people are pulling. The one that the 3 people are combining effort, you could see that one will be more fast and efficient in terms of the process. So we are saying that the tertiary carbocation, which we are saying they are the most stable, because that carbon with the positive charge is bonded to 3 other carbons, metal groups, and those groups are pushing electrons to neutralize the positive charge. And the more you're able to neutralize the positive charge, the more stable it becomes. So I'm saying that for examination's sake, you need to be able to identify a primary, secondary, tertiary carbocation of any compound I'll give to you. And then when you are asked to arrange them in order of increasing or decreasing stability, you can do that. Or if it's an objective test and then I have done different arrangements, you should be able to pick the correct order of arrangement. All right, so these are all more examples of the dehydration. Okay, but then there's another important thing you need to note here. Please, I hope you can all see my screen. Well, I want to explain something. All right. So now this is an alcohol. And this is the carbon that the OH, as the alcohol functional group, is attached. The previous examples I gave, you realize that there was only one carbon adjacent. That's where we remove the hydrogen. But in this instance, looking at the carbon that the OH is bonded to, you could see that there are 2 adjacent carbons. One to the left, this carbon, one to the right, this carbon. Okay. Now, in the 2 adjacent carbons, this one don't have any hydrogen here, but this one has a hydrogen. Okay. So if you remove this OH and then the hydrogen here, the double bond will come here. And that will give you an alkene. Now that alkene that you are forming will be 3,3 diameter 1 butene. 3,3 diameter 1 butene. Okay. But look at the 2 products here. None of them is the same as the one I have just mentioned. You are forming other alkenes. And in the case of the other alkenes, we are even calling the first one here as the major product and the other one the minor. Then the first one I talk about, that the double bond will come here, will also be a minor product. The question is why? The question is why? Now, there is something we call Wagner-Meilwen rearrangement. Wagner-Meilwen. Don't be frightened by the name. I'll do my best to see if I can explain certain things. Now, we initially says that the alcohol gets protonated. And then the second step, water molecule breaks off and form a carbocation. Now, when you form the carbocation, you have to be able to tell whether it is a primary, a secondary, or a tertiary. Now, in some instances, if you form a primary carbocation, we know primary carbocations are not that stable. So if you form an alkene from it, that alkene will also not be stable, and that letter will be formed. So if I want to form an alkene that is more stable, then the primary carbocation which I have initially formed, there could be what we call rearrangement. And that rearrangement is what I mentioned the name. Now, anytime there's Wagner-Mewen rearrangement, it leads to the formation of what? The most stable what? Intermediate carbocation. So after rearrangement from primary, you can rearrange to what? A secondary. If you have a secondary, you can rearrange to what? The tertiary, which is the most stable, before you form your alkene. So the rearrangement is geared towards you forming the most stable what? Product. Forming the most stable what? Product. The next slide I'm going to show will give maybe some, yes. Good. So you form your carbocation, and this one is a secondary carbocation. But the question is, forming this secondary carbocation, you can form an alkene from it. But that alkene will not be as stable as what? Forming it from what? A tertiary carbocation. So can we do a rearrangement so that we can form a tertiary carbocation before forming an alkene? And in this instance, it is yes. How do we do the rearrangement? We have two types. There's a hand up, so I don't know whether I should take that question or I should continue. Okay, let me take the question. Ilyasu, Yakubu. Ilyasu. Please go ahead, unmute yourself and ask your question. Wow. Albert, your hand is up. Okay, please. If there are no questions, just put your hand down, okay, so that the lecture can flow. Okay.
Oh, it seems he's offline.
All right. So those whose hands are up, please lower it. If there are no questions, let me continue. All right.
Hello, Doc.
Yes.
Yeah, please, with the diagram you just, or the slide you just showed us right now, where you said the OH is being break to form the double bond.
Mm-hmm.
Is it another form of isomerism, or because I can see that there are different names but the same structure?
Okay, what different names means? You mean the 2,3 diameter 2 butene,
Yeah.
and then the 2,3 diameter? Yes.
Yeah.
Yes. So don't say that they are not the same name. 2,3 diameter 2 butene is not the same as 2,3 diameter 1 butene. They are two different compounds, but they are isomers. They are structural isomers. The difference is the position of the double bond.
Okay, thank you very much.
All right.
Yes, Doc.
Yes.
Please, I want to know about the identification of the primary, the tertiary hydrocarbons. Like where you were explaining the second step. So you say there's a tertiary hydrocarbon there.
Okay, go and watch the week 1 recording. Okay, that's where we touch on primary carbon, secondary carbon, tertiary carbon, quaternary carbon. Then I show you primary hydrogen, secondary hydrogen, tertiary hydrogen. So when you get, you'll be able to identify carbons, and that previous knowledge will help you to appreciate these types of carbocations here. If we don't do it that way, we will not finish. We are supposed to start even our kinds today as to whether we can. This is week what? This is your week what? 3.
Said this week 3.
So but my questions will cover everything, whether we finish everything on up to the benzene or not. Questions will be asked on everything. So let's move, okay? And those who have issues, you can go and watch the video of the previous lecture. And then, let's move on. I will come back and then also throw more light. So now, after forming the secondary carbocation, I have indicated here that it is less stable. So if it is less stable, how do we make it more stable? So if a secondary carbocation is less stable, then we can only make it what? A tertiary carbocation, which is the most stable one. Now, there are 2 ways we can do that. You can either shift a hydrogen, an adjacent hydrogen, or an adjacent alkyl or methyl group. So here, you could see that this carbon, which is having the positive charge, which we are calling a secondary carbocation, there are 3 methyl groups, okay, which are adjacent to it. So we can move one of the methyl groups from where it is to this carbon that is having the positive charge. Now, when you move this methyl group here, then this carbon will now be having 4 bonds. And then the previous carbon where you move it from, that one will be having 3 bonds, as you can see here. And because of that, that carbon will assume a positive charge. Now, this carbocation here is a tertiary one, more stable than the secondary. So after doing the shifting a methyl group to the carbon here, and now the positive charge coming here, we are now forming a tertiary carbocation, which is more stable. Now, when you form the tertiary, then you look out for adjacent hydrogen. So when you take this one, this hydrogen here is adjacent to this. Then the ones on this methyl group is also adjacent. So you can remove this hydrogen here, and then the double bond will come in between these 2 carbons. And that is one of the products, which we are saying it is the major product. Then you can also remove one of the hydrogen here, and the double bond will come here, and that is this one, the A. So that is what you are seeing here. When you remove a hydrogen here, the double bond comes here and you form this. And when you remove it from here, the double bond comes here and you form that. Now, why are we calling this product the major and then this one the minor? This one is being called the major because that one is going to be formed more. That one is more stable than this one. Okay. So that brings us to the stability of what? Alkenes. Stability of what? Alkenes. Now, the more stable an alkene is, the more it is formed. How do we determine stability of alkenes? The most highly alkylated alkenes are the most stable ones. The most highly alkylated alkenes are the most stable one. Meaning, when you take the two carbons bearing the double bond, which of them has more alkyl groups on it? The one with more alkyl groups or alkyl chain is the most stable. So if you take the product here, these are the two carbons with a double bond. This carbon has what? 2 methyl groups. The other carbon here also has what? 2 methyl groups. So 4 different methyl groups. And this alkene is what? Highly alkylated, fully alkylated. That makes it more stable. Now look at the alkene up here. The two carbons bearing the double bond are these ones. Now this carbon here has this alkyl group here, 1, and then this alkyl groups here, 2. The other carbon do not have any alkyl group. There are only 2 hydrogens on it. So it means that this alkene has 2 alkyl groups as compared to the one down here, which has what? 4 alkyl groups. So it means comparing the two, the one down here is highly alkylated or highly substituted, and so it's more stable. And because it's more stable, it is formed more. And because it is formed more, it becomes the major product. And this one becomes what? The minor product. But then again, the two of them are formed from what? A tertiary carbocation, which is the most stable, compared to forming them from what? A secondary carbocation. So we move to the second method of preparing alkenes. And this one, you don't need an alcohol, you need an alkyl halide. Alkyl halide simply means that you have an alkyl residue in which one of the hydrogens has been replaced with what? A halogen. Either chlorine, bromine, fluorine, or whatever. So when you have an alkyl halide, in the presence of a base, you form an alkene. And here too, you are removing a hydrogen and a halogen. You are removing a hydrogen and a halogen. That's why we call it dehydrohalogenation. And the type of alkene you form is that the carbon that the halogen, so X here is representing all the halogens. It could be chlorine, bromine, fluorine. So the carbon that the halogen is attached is being removed with what? A hydrogen on an adjacent carbon. So you take away X and you come and remove one of the hydrogens here. Then between the two carbons, you introduce your double bond. And you form your alkene. This reaction requires bases and, of course, simple bases like sodium ethoxide, potassium ethoxide, and then other type of what? Bases. That is the mechanism here too. And we say the elimination reaction follows an E through. What it means is that you need a base that will pick on this acidic hydrogen. But let me ask a question. What makes this hydrogen acidic that a base can easily pick it? What makes this hydrogen acidic? Can somebody tell me? What makes this hydrogen acidic?
Because it has a positive ion.
Have we seen any positive ion there? Hello? Anyone? Yes. Nana. All right. So you see the alkyl halide, the halogen is highly electronegative. Okay. Is my cursor pointing to the halogen here?
No, please.
No,
No,
sir.
sir.
No, sir.
Sir.
So this is the halogen, right? Now, the carbon that the halogen is bonded to is called the alpha carbon. So the adjacent carbon is the beta carbon. So all the hydrogens on the beta carbon are what? Beta hydrogens. Now halogens are highly electronegative. So they draw electrons to themselves. They pull electrons to themselves. So whilst they are pulling electron crowd to themselves, they affect the electrons in the neighboring bonds because they are all being drawn towards where the halogen is. When that happens, the carbon hydrogen bond here becomes what? Weak. And when the carbon hydrogen here becomes weak, it makes this hydrogen what? Acidic, meaning it can easily be ionized. And so a base can easily react, acid base reaction. So far this is acidic, then the base will react with it. And the carbon hydrogen bond, this bond here, will break onto this single bond to form a double bond. Okay. So when this one breaks to form a double bond here, then this carbon will be having 5 bonds, which is not possible. So it means that the halogen has to break off, and then you form your alkene, and then this byproduct. So that is the mechanism there. So you can see 2 examples here where the bromine, which is a halogen, has to be removed with what? An adjacent hydrogen. This one is symmetrical, so it can go with a hydrogen here or here, and then you form your alkene. You form your alkene. What is important is that it requires a base or a basic medium for the reaction to take place. Now, to this elimination rule, that the halogen should be removed with an adjacent hydrogen, there is an exception to it. And that's what we call, there's an exception to that rule. The rule itself is the Caesar's rule, okay? So the Caesar's rule says that during an elimination reaction, the most stable, the most highly substituted alkene is formed. The most stable, which is the most highly substituted alkene, is formed. So whenever you are doing your elimination, that should be the guide. Now let's look at down here what is happening. The bromine is bonded to this carbon. Now that carbon has this carbon adjacent to it, and then this carbon adjacent to it. So it means the bromine can go with a hydrogen here, and then it can also go with a hydrogen here. If it gets removed with a hydrogen here, labeled the green color, okay, the double bond will come here, and that will form the B here, this alkene. Then when the bromine is removed with the other adjacent hydrogen, because there are 2 different adjacent hydrogens, and one of them can be removed with the bromine. So if it is a green one, the one labeled green, then it is this one that is forming. If it goes with this hydrogen here, labeled A, then it is this alkene that is forming. Now, this elimination we are saying is governed by Caesar's rule. So the question is, which of these 2 alkenes will be formed or will be prioritized? And of course, it is the first one, the top here. Why is this so? Because if you look at this alkene, the 2 carbons bearing the double bond, it's more alkylated. It's more substituted than the down here. What makes it more alkylated is because there are 1, 2, 3 alkyl groups and 1 hydrogen on it. But over here, you can only talk about 2 alkyl groups and 2 hydrogens. So I've already indicated that the stability of alkenes, okay, is dependent on its what? Substitution. If there are more alkyl substituent on it, or a more alkyl group, that alkene is more stable. And if a product is stable, then you have more forming, and that becomes the major product. So yes, these 2 alkenes will be formed, but then the 2-methyl 2-butene here will be formed more because that is the most stable alkene. The 2-methyl 1-butene will be formed, but that will be formed in little amount, and so that becomes what? The minor product. And this is governed by Caesar's rule, which says that during an elimination reaction, the most highly substituted alkene gets formed. But then there's an exception to this rule. And the exception is that if the base that you are employing, if the base that you are using is a bulky base, then the reverse takes place. Now, when we say a bulky base, we are talking about a base like potassium tetrabutanoxide or sodium tetrabutanoxide, something like this. It's very huge because the alkyl group is a lot. It's not just made up of 1 carbon. It's not made up of just 2 carbons. It's a lot. So it is very huge. So in that situation, you expect that it is the less substituted alkene that will be formed more. And you can see here, 72.5%. That one becomes your major product. And then the highly substituted alkene becomes what? Your minor product. So it's just the reverse of Caesar's rule. So in an exams, if I give you any alkyl halide and I give you a simple base, then note that the reaction will follow Caesar's rule so that you form the highly alkylated alkene as your major product. Because the question probably will tell you to give the major product. If the question says that give all the products, then you give the major and then the minor. Then, if the reaction I will provide for you involves a huge or bulky base, like the one you see on your screen, then that one, the reaction would follow anti, okay, it will be the opposite of the Caesar's rule. And then the least substituted alkene will be formed more, and that becomes your major product. So in an elimination reaction, pay attention to the type of the base being given to you in the reaction. So formation of the least substituted alkene using a bulky base. Bulky bases such as potassium tetrabutanoxide have difficulty removing sterically hindered hydrogens and generally only react with more accessible hydrogens. So the reason why when you are using a bulky base, it will prefer to give you the least substituted alkene is that the hydrogen that is supposed to be removed by way of Caesar's rule usually becomes hindered. It's overcrowded. So the bulky base cannot get access to it. Let me see if I can explain with this empirical situation. Let's say you are in a class and then you are a class of about 100. And then somebody enters your class and want to come and beat your course rep, there are two things that will happen. Either the class likes their course rep so much that they will not sit down for somebody to come and beat the course rep. So they will get up and then shield. They will surround the course rep. Now imagine about 100 people surrounding the course rep. It will be very difficult for the person to get access to the course rep to beat him or her. So that's what we mean by overcrowding. That's what we mean by hysterically hindered. It means that you are not accessible. The course rep is not accessible for the person to come and beat him or her. But if the course rep is not a good type and the class don't like him or her, when the person is coming to beat him or her, they will all stay away from him, even create enough space for the person to get access to him and beat him or her proper. Okay, so here there's accessibility. Okay, there's accessibility. So the same way we are saying that in the dehydrohalogenation reaction, the hydrogen that you are supposed to remove by way of elimination reaction, if that hydrogen is surrounded by a lot of groups, alkyl groups, then it becomes sterically hindered such that the bulky base cannot get access to it because it's huge. The space is small for it to get access to it. And so the bulky base will turn and look for accessible hydrogens rather and removed. And that will form an alkene, which is what? Less substituted and becomes a major product. So look at the condition at which the bulky base will give you the reverse. So these are more examples. You have the slide, so we'll go through. The last method of preparing alkenes so that we can go to the reactions. The last method of preparing alkenes is the debromination of vicinal dibromides. And this one is very simple. So you could see that when we say vicinal dibromides, it means that there are two bromines on adjacent carbons. Okay. There are two bromines on what? Adjacent carbons. So we also need a base. And the base normally that is used is what? Sodium iodide in acetone. And then the base will pick on the bromine. This bond will break here, form another bond, and other bromine will break away. So in simple terms, the two carbons that is bearing the two bromines, you are removing the two bromines and then you introduce a double bond there and you form your alkene. That is debromination. So as for debromination, just identify a vicinal dibromide, and in the presence of the base, you are removing the two bromines, and then in between the two carbons there, you introduce your double bond. Apart from the sodium iodide in acetone, you can also use zinc in acetic acid or zinc in ethanol. And I indicated this right from the beginning of the class that where we have gotten to, pay attention to starting material, pay attention to the reaction conditions, and then the expected product. So for the dehydration reaction, these are all reagents that can be used. Okay, any one of them you can use, and then you are right. Okay. So either you use sodium iodide in acetone, or use zinc in acetic acid, or use zinc in what? Ethanol. It performs the same function and you form your alkene. So now that we know how to prepare alkenes, now we need to know how alkenes react. We need to know how alkenes react. So the reactions of alkenes, okay, or the chemical properties of alkenes, that is the next area we are going to look at. And here too, it involves you paying attention to the starting material, which is going to be the alkene, and then the different conditions that the alkenes will react, and then the expected product that you are supposed to form. Please, we are breaking briefly per my watch. It is 8:43. We are coming back exactly at 9 a.m. and then continue with the chemical properties of alkenes. And then if we are able to finish with that one early, we can start with the alkynes. So please, we're breaking for some few minutes. Let's take some walk. Let's go and stretch. Let's go and sip some water. Let's go and take some cocoa, and then we come back. All right, I guess we are all back.
Yes, sir.
All right, so looking at the chemical properties of alkenes, we are looking at how alkenes react under different conditions. But then the question we want to ask ourselves is, we got to know alkenes are non-reactive. Okay. But how come that alkenes are very, very reactive? And the reason is that the presence of the double bond, which is made up of one sigma bond and then one pi bond. The electrons in the pi bond are readily available, and so they are loosely held, and those electrons makes alkenes nucleophilic. And for that matter, they can easily react as compared to the alkenes without necessarily the provision of what sunlight or heat, which were the requirements under which alkenes can react. So for alkenes, the typical reaction that alkenes undergo is electrophilic addition reaction. Electrophilic addition reaction. When we say electrophilic, from the word electrophile, that is a species that is what electron deficient, can be added to an alkene because the alkene themselves are nucleophilic. They are electron rich. What makes alkenes electron rich is because of what? The second bond in the double bond, which is the pi bond, that contains the pi electrons, and these electrons are readily available for reactions. So that makes alkenes reactive. We'll be looking at a number of reactions. So the electrophilic addition reaction, an overview is what you can see. And the alkene, because of the pi bond with the pi electrons, it becomes electron rich. And because it's electron rich, it is nucleophilic. So whenever it sees an electrophile, a positively charged species, the nucleophile will react by way of adding the electrophile to it itself. And that's what we call electrophilic addition, adding electrophile to the alkene. Of course, the double bond, the pi bond with the pi electrons will break before there is the addition of the electrophile. So you get this intermediate, and then and nucleophile. Of course, in the reactions of the alkenes, we are seeing the intermediate carbocation again. So when you form the carbocation, then a nucleophile can then react. So it's like in chemistry, positive, negative, and then there's a reaction. You create a positive center, a negative center, and then there's a reaction. So that is basically that. So most of the reactions of alkenes we'll be looking at follow electrophilic addition reactions. And the common ones are hydration of alkenes to form alcohol, hydrohalogenation of alkenes to form alkyl halides, hydrogenation of alkenes to form alkanes, oxidative cleavage to forming carbonyl compounds, epoxidation, and halogenation. So these ones are the common ones. We need to look at them briefly, maybe in the next 1 hour, and then we can move to the alkynes. For the hydration, you have an alkene and you add water to it, you form an alcohol. Remember, in preparing alkenes, we were using alcohols and we were removing water. So it's like the reverse. I have an alcohol in the presence of an acid catalyst, I'll remove water and form an alkene. If I have an alkene in the presence of an acid catalyst, I can add water to it and form back my alcohol. So the dehydration of alcohol to form alkene and then the hydration of alkenes to form alcohol is just the reverse. Then the hydrohalogenation we saw the dehydrohalogenation where you remove a halogen and the hydrogen to forming alkene, elimination reaction following Caesar's rule. And so if I also have an acid halide, it could be ACl, HBr, I can add the same thing to an alkene and form back my alkyl halide. Hydrogenation, we're adding hydrogen to an alkene in the presence of a metal catalyst, which could be nickel, platinum, palladium, palladium. And then the alkene will absorb a molecule of what? Hydrogen and reduce the double bond to what? A single bond to form the saturated alkene. Of course, oxidative cleavage, the double bond can be cleaved so that you form two fragments under certain conditions. Then halogenation, you can add a halogen to an alkene and you form a dihalo compound. A very common illustration of the halogenation is the addition of bromine carbon tet or bromine water to an alkene, which you observably will see the decolorization or the fading of the brown color of bromine to colorless. That tells you that there's a double bond which is reacting with your bromine carbon tet or bromine water. So we are looking at all these reactions one after the other, and then we see the next step. So the first one is addition of hydrogen halides to alkene. And when we say hydrogen halides or halogen acids, the common ones are HI, HBr, ACl, and HF. When these halogens are bonded to hydrogen, we call them the hydrogen halides. We call them the hydrogen acids. How do they react with what? Alkenes. How do they react with what? Alkenes. Now, we've already indicated that the alkenes are nucleophilic. Why are they nucleophilic? They are electron rich. What makes them electron rich is because of what? The double bond, the pi bond, okay? The pi bond with the pi electrons. The electrons are readily available. So it makes the whole alkene what? nucleophilic. Now, these acids are also what? Electrophilic. They are able to produce H plus ions. So it means that the alkene can pick on the hydrogen to itself, and then you form your alkyl halide. Now, this reaction is governed by what we call Markovnikov's rule. Is there anyone here who can help us to state Markovnikov's rule? Anyone here who wants to help us state Markovnikov's rule? What is Markovnikov's rule? Yes. Hello. Or is it the first time you are hearing Markovnikov's rule? I'm not sure. Or this one, even back in secondary school, it was one of the common rules. Is there anyone here who didn't do chemistry at the secondary school level?
We did do, but
I've forgotten.
yes, sir.
So many years ago.
My first time of hearing it. It's okay. It's okay. So let me find out if somebody can help us to state
Over 28 years ago. Over 28 years ago.
Hey, yeah. Now, how old are you?
It's okay. Whether it is 2 decades or a decade or 3 decades, we are still here. There's a saying that there's no end to learning. We keep on learning and learning and learning until eternity. So Markovnikov's rule is saying that if you are adding a halogen acid, and you can see the examples on the screen, the halogen acids, if you are adding any one of them to an asymmetric alkene, when we say an asymmetric alkene to, I don't know whether you know what it is, but you see some alkenes are symmetrical, meaning the double bond is in the middle. So if you cut it into 2 equal halves, it's going to be possible. That's the symmetrical. The asymmetric, you realize that the double bond in the structure is not situated in the middle. Okay. So Markovnikov is saying that when you are adding a halogen acid to an asymmetric alkene, the hydrogen from the acid goes to the carbon with more hydrogen. The hydrogen from the acid goes to the carbon with more hydrogen. If you do the opposite, then we call it what? Anti-Markovnikov. Anti-Markovnikov. We will later find out soon the rationale or the significance behind Markovnikov's rule. So you can see on your screen that initially the alkene had a double bond, and then you added a halogen acid, and so the hydrogen from the acid has been added. That's the one in blue. Then the halogen is also added, the one in red. But this addition had taken place, and of course, the double bond is then gone. You cannot add this fragment or this component and still maintain the double bond, because note that carbon should always have 4 bonds. So the double bond get reduced, and then the 2 carbons that are bearing the double bond, one of them picks on hydrogen, the other one picks on the halogen. In a symmetrical system, this is straightforward and not a challenging at all. But in an asymmetric system, then that's where Markovnikov's rule comes in. Where should the hydrogen go? Where should the halogen go? And the rule says that the hydrogen should go to the carbon with more hydrogen, and then the halogen goes to the other carbon. This particular rule, McConaughey's rule, is synonymous or is similar to the biblical saying. Those of you who are Christians, there's a biblical saying that in the gift of the Spirit, when you are given the spirit of teaching, or when you are given the spirit of prophecy, or when you are given the spirit of healing, and then you use it well, you are giving more. To them that has more is given. So it means that if you are adding a halogen acid to an alkene, there are two carbons that bears the double bond. Look out for the one that has more hydrogen, and then the hydrogen from the acid goes to that side, then the halogen goes to the other side. And that is McConaughey's rule. And like I said, you will get to know the significance of McConaughey's rule soon. So look at this example here. You see that here, the double bond is not in the middle. If you cut this into two equal halves, on your right side, there are two carbons. On your left side, there's one carbon. So this one is what? Asymmetric alkene. So when you're adding HBr, hydrogen bromide, then the hydrogen from this HBr should go to the carbon with more hydrogens. Now look at the two carbons bearing the double bond. Which one has more hydrogens? Is this one, isn't it?
Yes.
So the hydrogen from the acid here should come here, so that now the two hydrogens here will become what? 3. Then the bromine then goes to the other carbon. So it comes here, and that gives you this product, 2-bromopropane. Now, if you do the reverse or the opposite, that is, if you don't follow McConaughey's rule, but you decide that the hydrogen from the acid should go to the carbon with few hydrogen, that's here, so the halogen comes here, that gives you this product. And a little of that product gets formed. A little of that product gets formed. So we still have another example down here where these two carbons are bearing the double bond. So if I am adding hydrogen bromide, which of the carbons has more hydrogen? It is this one. This carbon has 2 hydrogens. This carbon has no hydrogen on it. So the hydrogen from the HBr will come here, so that here will become what? CH3. Then the bromine will come here, and then that will give you this product. If you do the reverse, that will be the minor product. Now, who can tell me the rationale behind McConaughey's rule? Why should the hydrogen go to the carbon with more hydrogens and then the halogen go to the other side? What is the significance of McConaughey's rule in terms of product formation? What is the significance of McConaughey's rule? Yes, class.
The high electronegativity of the halogen
has done what?
I think that is why it would have to. I'll come back again.
Did you take cocoa during the break time?
Yes, I did.
Oh, then you should give a better answer, because the answer you are giving me shows that maybe the cocoa was not enough. Yes, Ebenezer. Ebenezer, try.
Okay, Doc, in my opinion, I think the rationale behind the McConaughey rule is for us to make more stable carbocations.
Yes. the rationale is geared towards you forming the most stable intermediate carbocation. But why is it so important to make the most stable intermediate carbocation? Yes. Yes, Richard Appiah. Yes. Richard, we can't hear you. Hello. Any other person? Well, I've explained this thing today, in terms of stability of product. That in chemistry, when you are forming a product and the product is not stable, little will be formed or none at all. And when the product that is forming is stable, then you form more, and then we have a good yield. And that the product formation is also dependent on what the intermediate product. If your intermediate is stable, then the final product will be stable. If the intermediate is not stable, then you will not be stable. So Marconico's rule is for you to form the most stable intermediate product, which is the carbocation, so that you can form the most stable product at the end of the day. So that's the significance of the Marconico's rule. So the mechanism is there just to help you appreciate what's happening. But like I said, I will not tell you to come out to the mechanism. So the screen that you are seeing, you could see that if you add the hydrogen, first of all, if you add the hydrogen by Marconico's, then that will give you the secondary carbocation. Primary and secondary, which one is more stable? It is the secondary. So Marconico's rule always leads to the formation of what? The most stable intermediate. Whilst the anti-Marconico's always leads to the formation of what? The least stable what? Intermediate. And then consequently, your product that is forming, the one that is formed from the secondary carbocation is formed more. So that one becomes the major product. And then the other one becomes what? The minor product. What you see is still giving you more examples, more illustration. So you are adding a halogen acid to an alkene. Now the alkene, the double bond is always between two carbons. So which of the two carbons is having more hydrogen? Is this one? So the hydrogen, the blue one should come here. Then the halogen, the bromine should come to the other carbon. And that gives you the major product. If you do the reverse, that one is the anti-Marconico's product, and that is always forming smaller amounts. But then there is an exception to Marconico's rule. Like we saw the exception to Caesar's rule, there is also exception to Marconico's rule. And the exception is that whenever you are adding the halogen acid and you do so in the presence of a peroxide, then the reaction will not follow Marconico's addition. It will rather favor anti-Marconico's addition. And so the minor product, which we had seen in the Marconico's addition, then becomes the major product. And the major product becomes the minor product. So under the exception to Marconico's rule, which is addition of a peroxide apart from the halogen acid, the major becomes the minor, and then the minor becomes the major from the Marconico's addition. So always pay attention to the reagent, and if the HBr is added under peroxide, then you should know that it's going to favor anti-McConaughey's rule. And this anti-McConaughey's addition only occurs when hydrogen bromide is used. Only occurs when hydrogen bromide is used. Hydrogenation of alkenes is very simple. Now you have an alkene, a double bond. You want to form an alkane. So you have to reduce the double bond to a single bond. How to do that is by the alkene absorbing a molecule of hydrogen under a metal catalyst. Please, it's not important to bring all the metal catalysts there, but any one of them, either nickel, palladium, platinum, palladium, cobalt, any one of them. So it's hydrogen under any of these metals, then you form your alkene. And that's hydrogenation of alkenes. So catalytic hydrogenation in the presence of a metal catalyst will lead to the formation of an alkene. So this is an alkene. It absorbs hydrogen under a metal catalyst, and then you form your alkene. Then the next reaction of alkenes is addition of water, which is hydration. Remember, we have looked at dehydration. So we had an alcohol and we remove water and we form an alkene. Now we have the alkene and we are saying that we can add water to form back our alcohol. But in both instances, we needed an acid catalyst. In both instances, whether it is a dehydration, removal of water to form an alkene, or hydration, addition of water to form an alcohol, we needed an acid catalyst that helps to speed up the reaction. So as you can see on the screen, there is this alkene, and then you add water and the acid, and then you form your alcohol. I have a question for the class based on what you see on the screen. Are you ready for the question?
Yes, sir.
Okay. Can alkene react with water? That's my question.
Sir, please, the question again.
Can an alkene react with water?
No, please. I don't think so.
Say no. But on the screen,
No, sir.
On the screen, we are saying addition of water to alkenes. That is hydration, and that will form an alcohol. Why are you saying no? Can you explain?
They can only do that in the presence of a catalyst, which is an acid catalyst.
They can only do that in the presence of an acid. Good. So my other question is, why can't water react with an alkene?
So because water is non-polar. Water is polar. Alkene is non-polar.
Please relax. Come again.
I was saying that alkenes are non-polar.
Alkenes are non-polar.
But water is polar.
Water is polar. That's why they cannot react unless
there's yes.
Okay, Jefta, but my question is about reaction. It's not about solubility. Okay, what explanation you have given is right, but then it applies to solubility because water is polar solvent. It cannot dissolve a non-polar compound, which is alkene. So when you add water and alkene together, the two will be immiscible, and the water will be down because it's denser than alkene. So that one is solubility. I'm talking about reaction. Yes, Bright.
All right.
The alkenes will not react with pure water since water is not acidic enough to allow the hydrogen to act as an electrophile to initiate the reaction.
Oh, there's some background noise. So, all right. So,
hello.
Yes.
Hello.
Yeah, go ahead.
I was saying that the alkene will not be able to react with pure water since water is not acidic enough to pave a way for the hydrogen to act as an electrophile to initiate the reaction.
Sir, and
Hello,
also,
hello, sir.
yes, hello, sir.
Yeah, Jefta.
You know, also earlier on you mentioned that alkenes they have the pi bond. So with
Yes.
water, with water, water is like the nucleophilic ability of water is weak. So when it is so, it cannot react with the pi bond.
You see, I don't know whether I've said this, but then if I've not,
Hello,
let me just
hello.
indicate it. Let me just indicate it here, okay? You see, everything about chemistry is about real life situation. Though there are some abnormalities in real life situations, but in real life situation, a male gets attracted to a female, isn't it? And then they get attracted. Now, in chemistry, whenever there's a positive and a negative charges, there's a reaction. If you have two negative charges, they will not react. If you have two positive charges, they will not react with each other. If you have two males, they cannot be attracted to each other. They will repel. If you have two females, they will never get attracted. They will be repelling each other. Though we know of some abnormalities where now females go for females. Those ones are not normal. Okay. So all that we are saying is that chemistry in context here, and when we talk about reaction in chemistry, the two most important things is creating a positive center and then what? A negative center. Now, we've already said that the alkene is nucleophilic, isn't it? It means it is electron rich. It's a negatively charged species. Then the water too is also nucleophilic, isn't it? Because of the lone pair of electrons. The water too is also what? Nucleophilic. So you have two nucleophiles. It's like female. They will not react, they will repel. So it is only under an acid condition, then the alkene will first of all will react with the acid and form a carbocation. And now the carbocation becomes a positively charged before the water can then attack it. So yes, water and alkene cannot react unless there is an acid catalyst. The reason why they cannot react is that both are all nucleophiles. Both the alkene and the water are nucleophiles. And so that is the reason. Can we continue?
Yes, sir.
All right. So the mechanism of what I've just done. So the acid will first of all will react with the alkene. But the acid is a electrophile. The alkene is what? Nucleophile. So that will react and then you form a carbocation. After forming the carbocation, now the carbocation is positively charged. So it is what? An electrophile. Then the water is what? A nucleophile, electron rich. Before the water can then come in and then you form your alcohol. You form your alcohol. So that's the mechanism to explain what I've just told you. So now I have an alkene, I have water and an acid, so I'm supposed to form an alcohol. Now we say that the reaction follows Marconico's rule. So you expected that the H plus from the acid should come to this carbon. Then the water, the OH from the water will come to this carbon and you form an alcohol. But then what we have here is different. And the reason is that when you add the acid proton here and it becomes CH3, then before the water comes in, you are forming a carbocation. And that carbocation here is a secondary carbocation. Okay. Now, when you form a secondary carbocation, the water can come in and you form that alcohol. But that alcohol will be a minor product. But if you are forming a secondary carbocation here, you can do 1-2 meter shift. Okay. You can shift one of the metal groups here, and then the positive charge will come to this carbon, and that will be a tertiary carbocation. And that tertiary carbocation, the water will come there, and then you form this particular alcohol. And that is the major, because it is being formed from the most stable intermediate carbocation, which is tertiary, as compared to the previous one. So the reaction involves the formation of a carbocation in the first step. The carbocation rearranged to a more stable one if that arrangement is possible. In this case, yes, it is possible, because the initial carbocation you formed was a secondary, and then you can do 1-2 meter shift. Shift one of the 2 meter groups here, and then the plus will come onto this carbon, and that one is a tertiary carbocation before the water comes in, and then you form your alcohol. Now, if you don't want this rearrangement to the most stable carbocation, then you use what you call oxymecration demecration, meaning the addition of the water should not be done in just an acid. Okay, the addition of the water should be done in what? Mercuric sulfate, and then that will prevent rearrangement. In that case, the secondary carbocation that you initially will form will give you a good yield of what? An alcohol. The water will react, and then you form an alcohol, and that will be 3,3 diameter 2-butanol. 3,3 diameter 2-butanol will be your, that is if you do oxymecration demecration. So note the addition of water. It can be done in an acid. That one allows for rearrangement to the most stable intermediate carbocation. But if you want to prevent this rearrangement, then please apply oxymecration demecration. And the reagent in here is that you are adding water, but then you are adding the water in mercuric sulfate. So the oxymecration demecration allows the Markovnikov addition of hydrogen and OH without any rearrangement taking place. Without any rearrangement taking place. Addition of bromine and chlorine. And this one, once you move to the secondary school to teach, there is this chemical test that is very common, and it's a test for unsaturation. And this reaction explains the test for unsaturation. If you have an alkane and you have an alkene, and you are asked, how do you chemically differentiate between the two? Then you can use this reaction. Okay. Alkanes do not react appreciably with bromine or chlorine at room temperature, and then the absence of what? Light. The alkanes react rapidly with chlorine and bromine without light or heat. So if you have an alkane and then an alkene, then you can use bromine in carbon tete to distinguish or differentiate between them. You can also use bromine water. How does alkenes react with bromine in carbon tete? You will see that the double bond, the 2 carbons bearing the double bond, you reduce the double bond to a single bond, and then you have the bromine getting itself attached, to the 2 carbons, as you can see here. Now, in the lab, the bromine has a brown color. Bromine carbon tete, it has a brown color. So when you add it to the alkene, one physical way you will see that the reaction is taking place is the decolorization of the brown color of the bromine. Is the fading of the brown color of the bromine. So the reagent has a unique brownish color. So when you add it to the alkene, because reaction will start, you will see that the brown color solution begins to fade away, it colorizes, and becomes colorless. So the colorless is the dibromo compound that is formed after bromine reacts with what? An alkene. This same reagent, when you add it to an alkane, okay, when you add it to an alkane, the brown color of the bromine will persist. The brown color of the bromine will not fade away. It will not decolorize. You will still see. That should tell you that the bromine water or the bromine carbonate is not reacting with the alkane. And so that is one simple chemical test that can be used to distinguish between alkane and then alkene. The mechanism is here. When you have time, you can look at it. So this is just the equation for the test for unsaturation. They react with both alkyne and alkene. So the brown color of the bromine will become colorless after the bromine had bonded to the two carbons, which initially had the double bond. But then the double bond and the triple bond do not stay. After the addition reaction, you form single bonds. In the case of the alkene, there's only one pi bond we are breaking, so we need only one molecule of the bromine in carbonate. In the case of an alkyne, there are two pi bonds that you have to break to get to the single bond. So you need 2 moles of what? The reagent, the bromine carbonate. And that is the test reagent for unsaturation. Alkenes react, alkynes react, but alkanes do not react. All right, so another reaction, and probably that might be the last but one, oxidation of alkenes. Now, oxidation of alkenes, that's a double bond, can be done using cold potassium permanganate or osmium tetraoxide. That one forms what we call the glycols or the diols. So please pay attention. Cold oxidation, mild oxidation do not cleave a double bond. Rather, it reduces the double bond and you form a diol. So the 2 carbons that bear the double bond, you reduce the double bond to a single bond, then you add 1 OH here, you add another 1 OH here, and you form what? Your diol. So the condition is what? Cold, mild, KMNO4. And you can also use osmium tetraoxide and pyridine, okay, to also form a diol. Okay, osmium tetraoxide also forms a diol. This is what we call the mild oxidation. But when it comes to the vigorous oxidation, oxidative cleavage, that one, you don't form a diol, you cleave the double bond and you form 2 fragments. You form 2 fragments. That is this one, oxidative cleavage. So alkenes with monosubstituted carbon atoms are oxidatively cleaved to source of carboxylic acids by hot basic permanganate solutions. So here you can see that this particular oxidation is not mild, it's not cold because of the presence of what? Heat. So the reaction condition here in alkaline solution means that the double bond has to break. And when it breaks like this, the left side becomes 1 fragment, the right side becomes another fragment. And in both cases, you form an acid if it is a mono-substituted alkene, meaning the 2 carbons bearing the double bond had hydrogens each to themselves. So you form carboxylic acid. If the 2 carbons bearing the double bond do not have hydrogen, that is their di-substituted, then you form a ketone. You form a ketone. And of course, if the fragment break. You see the side here labeled green because the carbon do not have any alkyl group on it. It's just two hydrogens. That side will always give you carbon dioxide. That side will always give you carbon dioxide. So usually terminal alkenes after exhaustive oxidation always leads to the evolution of what? A gas. And the gas is what? Carbon dioxide. Now this portion, the carbon is not having any hydrogen. So that side will give you what? A ketone, as you can see here. So again, the type of alkene determines the type of product you form under exhaustive oxidation reaction. So apart from the bromine in carbon tet, we can also use the permanganate solution to test for alkenes and alkynes. When you add potassium permanganate to an alkene, it will react. The purple color of the permanganate will change to brownish PPT, and that tells you that there's what? An alkene or alkyne present. The last reaction of alkenes, and we are done with alkenes, is ozonolysis. Ozonolysis, like the exhaustive oxidation, also cleaves a double bond. Just that the ozonolysis is a mild oxidation, which cleaves a double bond to form an aldehyde if it is monosubstituted alkene, or a ketone if it is what? A disubstituted alkene. So alkenes react vigorously with ozone to form the ozonides, and then the ozonides then after catalytic reduction will form the aldehyde or ketone. So that is it. So ozonolysis, you need an ozone in dichloromethane, and then followed by catalytic reduction. So here the reagents are a lot, but you try as much as possible to remember them. And the more you go over, the better it sticks. Okay, so don't go and sleep and say that organic chemistry, the reagents are many, I can't remember. Oh no, don't sleep. Wake up at night, okay, and then go through, and then you'll be fine.
Enough for more.
Enough for more. So these are more examples of ozonolysis reaction. You see that I have labeled the two fragments. This side is red, this side is green. So when you cleave the double bond, okay, this side that is labeled green, because the carbon has one hydrogen, that will form an aldehyde, and that is the aldehyde, acetaldehyde. Then the side labeled red, when you cleave the double bond, because the carbon here, the alkenic carbon did not have any hydrogen, that side will form a ketone, and that's acetone. Okay, so that is ozonolysis for you. So that brings us to the end of the reactions of alkenes, and of course alkenes in general. So we will have to start with the alkynes. So if you are ready, I will continue with the alkynes. Are you ready? No response.
So I think some people have raised their hands for
No,
questions.
no. Okay, so I will take 1 or 2 or 3 or 4 questions on the alkenes, and then we'll close the docket, and then I will have I shared the lecture slides on the alkynes with you. I think I shared with the course reps.
Yeah, sure.
Yeah. So I will we'll start with the alkynes, and then because ideally with 3 we should have been finishing with alkynes, so we are behind. The next week, which is your last meeting, we should be able to also touch on the aromatics. That is the benzene chemistry, and that is a lot. I will share the slide with you so that you, on your own, you can begin to read them yourself. It's not everything that we will talk about here. Some things you have to also create time and then go watch some YouTube videos, and then do some group discussion, learn from your friends. You know, at the university level, it's all about ideas, sharing of ideas. Nobody knows it all. So please don't stay in your room alone and learn organic chemistry. You will fail. You will fail. Okay. Yes. So let me take some questions and then.
Yeah, we are far away from each other.
Oh, but you are center based. Those of you who are at Akrade, if you are about 20, you can get to know yourself. But now you should be having your center based WhatsApp platform. Those of you who are in Sunyane, if you are about 15, you should be meeting together. Those of you who are in Bolga, if you are about 5, you meet together. Those of you who are at Kaswa, if you are about 30, you should know. You should have a common platform so that you can also be learning among yourselves.
So when you call out, nobody gives a response.
Don't
when
worry.
You call out for them to Saturday, nobody will mind you.
Don't worry. After they've rated the quiz 1 and they get 0, they will start managing you. Okay.
My God, so sad.
Wait, don't worry. Very soon.
First degree in chemistry.
First degree, you do some chemistry, eh?
Yes, sir.
What program was that?
Chemistry. Chemistry. We're having chemistry 2 and chemistry 1.
Okay, so the point is that like some of you are saying, it's been 2 decades, 3 decades, so you might have forgotten. Then again, maybe those days there are a lot of challenge, there are a lot of issues coming up. Revision of the course content, and new ideas are coming, and you expect to know and get abreast with what modern day organic chemistry. Okay.
Hello, Doc. Please, Doc.
Please ask question on the slide and let's move on.
Hello, Doc.
Yes, yeah.
Yeah. Please, Doc. This medium we are using, we use this in Google Meet. And just as you said a couple of minutes ago, that you should go over and over. No? You would have loved if it were Zoom. Some of us could have recorded it.
Oh, the center, the e-learning unit is recording, so they will give it to you. Okay.
That one is on YouTube, and download it. You can't download it unless you always use data to watch it. That is also draining us a bit.
Oh.
If you have it on the Zoom, you get it as soon as you download it on a Telegram. You can even watch it. Some of us are far the opposite of East Legon.
Okay, so maybe I'll find out from the e-learning unit if they can upload this on what's the platform?
Telegram.
Yeah, Telegram. Okay.
So that you find if they Telegram platform, you get it there.
Yes, but you people can start creating a Telegram.
Thank you very much, sir.
Okay. So so now there's no question. So let me start with that time.
Hello, sir. Hello, sir.
Yes.
So please, the slide on the alkyne is not on the page. Oh, you can share it again.
I share with some of the core crops.
The slide is there. If you want it, you can DM me so I can send it to you.
You should send it to the page rather than not necessary for.
Yeah, please can you send it to the page?
Is it the chemistry page or the general page I should share?
Please send it to the general.
Say the chemistry page.
There's somebody to try and post it for us.
Okay, let me send it.
I've shared it at the chemistry page.
Okay.
So please try and then download it and then
Those
let's
in
add
chemistry major, if you have it, just post it so that those are at the minor side, you will get it. Not all of us are on the chemistry major platform.
Exactly.
Sir, please, I think this introduction to organic chemistry is for both chemistry major and chemistry minor. So most of the times, when you share it on the chemistry major platform, we do not get those doing the chemistry minor. We normally do not get it.
Okay. Please let me chip in. So right now, which slide do you want? Is it the alkynes or the alkenes?
So what is on the screen is the alkenes. Now we are done. I've shared alkynes.
Okay, so I'll send it to the biology.
And also the review.
Yes, I think that's good.
And also the review question that Doc said the last time that you be sharing with the chemistry people. As of now, you will not receive it on our platform.
The main platform.
So they should share that one.
Hello, sir.
Please. Yes.
Sir, please, I have a question.
Yes, ask your question, please.
Please, what could be the form of question you can set on these things you were doing, like there's analysis and force?
Okay, so like I told you from the onset in today's lecture, that where we've gotten to now, okay, organic chemistry is the easiest of all the chemistry aspects. Okay, very easy. It's like drinking cocoa. Okay. Very easy.
Okay.
But then it's a lot. Okay, it's like you have a lot of things to be content with. So the more you practice, the better. So I've told you that where we've gotten to the reactions, that is where the headache is. There are a number of reactions we are going to look at, a number of them. But what can help you is that, or how I do ask questions is that I can give you the starting material, give you the reagent and then the condition, and then tell you which product is going to be formed. I can give you the starting material, and then I'll give you the product, and I'll tell you what reagent or condition can do this conversion, can convert this starting material to this product. So you then have to give me the reagent. Is that right? So that's how questions will be asked. So if any of the reactions that you see, like the one you are seeing on your screen, the ozonolysis, you know that, oh, at the left side they all alkenes, okay? Then at the right side, these are aldehydes or ketones. How do I get an aldehyde? How do I get a ketone? Do you understand? Now, the aldehydes is when you have the carbon, where you are doing the cleavage. The carbon has one hydrogen. That fragment will form an aldehyde. Now, the side of the carbon, the double bond carbon, which has no hydrogen on it, that side will give you a ketone. Then the next thing is that, hey, what is the reagent for ozonolysis? Ozone, O3. Okay, followed by reduction, zinc in acetic acid. So you just pay attention, but in the multiple choice questions, I'll even will give you all the various reagents that you could choose from. So you should try and be very conversant with some of the reactions, so that when you talk about ozonolysis, you know that, oh, this is the reagent. When you talk about maybe addition of halogen acid, this is the reagent. So that's how it's going to be like, okay?
All right, sir.
But I'm sure you know the format that your quizzes are all going to be 20 multiple choice, okay?
Yes.
1 and quiz 2. The end of semester, I'll bring 20 multiple choice and then some subjective questions, about 4, and you choose 2. And that's where you'll be doing some small writing, and then you'll be okay. You'll be fine.
It should be simple though.
With me, you will be okay. So, yes.
All right. Doc, please, I want to know, apart from these slides, what other materials are we recommended to do our
Albert, there are a number of chemistry textbooks that talks about all that we are doing here. Okay.
Can we go back and check our senior high school subs and corps? Can we use it?
Albert, in fact, when I was in secondary school, somewhere 1998, 99, I used sub-series, okay? Core series was there, I use sub-series. But I don't really have an idea the content now to tell you that it has enough information for this course. Now I can't tell. I can only prescribe that Solomon's is a textbook. You can download it online, but if you download Solomon's, which has over 2,000 pages, and look at how intensive this program is. By the time you are done learning from the Solomons, that will be about some years now. Okay, so that's how come. I don't want you to go and waste so much time. Now I have given you lecture slides. It is my responsibility to give you lecture slides, lecture materials. These are summarized form. But if you want to go and read more, yes, I can. Did I give you have I given you the course description? Or I think I gave the course description outline too. I have outlined some textbooks, okay, that you can also refer, make it as a reference material to understand more. Okay, so yes, please don't go and limit yourself to core series or sub-series. Get chemistry textbooks, okay. First edition is there. Solomon's 9th edition is there. And then I have written a model for code. I don't know whether I've shared that one. Maybe I can share that one too, because it has a number of my questions in there. Okay, the code model. I will share a soft copy with you after the class. Okay.
Yes, we like that one.
And that one is detailed, and I think that one too can be of help. Okay.
Thank you. Thank you.
It's better. Those in the major group. When the question is shared, kindly let's just have it. Those in the chemistry major group, please, we beg. When the question is shared or any slide is given, kindly give it to all of us.
First is you are biology major, eh?
Yes, so you don't get it. You don't get it.
No, so I will share also on the main page if so that all of you get. Just that on the main page, because I don't know whether all of you are doing this course, but don't worry, I will share them there so you can get it.
Okay.
Okay, Doc.
Okay,
thank you very
much. Oh, Doc, I have one question.
Yes, please ask, and then let me start with the alkynes.
Okay, sir, please, on the addition of the hydrogen halide to the alkenes, sir, when the question is being given to us, should we go with the main product or the little formed? Maybe you give us the reactant and with the condition for us to write the product. Should we write the major one or the little formed?
Okay, so the question will let you know which one is needed. Okay.
Okay,
sometimes just pay attention to the question and understand. You could see my choice of words, and I'll ask, what is the predominant product? What is the principal product? What is the major product? So here, the choice of words as I'm using will tell you that the answer that I'm after is not just any other product, not the minor product, but then it is the major product, the principal product, the predominant product. I hope that is clear.
Yes, please. Thank you.
If the question is subjective, and then I want you to write all the possible products, I would also indicate, list all the products that can be formed from this reaction. In that case, both the major and the minor should be captured for you to score.
Okay, sir. Thank you.
Welcome. So hydrocarbons contains carbon and hydrogen only. And we said we have the aromatic hydrocarbons as a benzene and the group. Then we have the aliphatic. The aliphatic, we had the saturated, which is the alkanes. We are done with the alkanes. Then we have the unsaturated aliphatic, which is the alkenes and alkynes. We just finished with the alkenes. So we are looking at the alkynes, and then When we are done with alkynes, we will then look at the aromatic hydrocarbons, and that will bring us to the end of this course. So alkynes, which are unsaturated hydrocarbons, are characterized by the presence of what? Carbon-carbon triple bond. So as soon as you see a carbon, triple bond carbon, that tells you that the compound is what? An alkyne. Okay. The double bond is an alkene, the triple bond is an alkyne. So if somebody asks you, what is the functional group of an alkyne? It is a carbon-carbon triple bond. That's the functional group. Now, the carbon atoms in alkyne are in S. Hey, I say more. Please mute yourself. The carbon atoms in alkynes are in sp hybridized state. We got to know that the alkanes, the carbons are sp3 hybridized. The alkenes, they are sp2 hybridized. And then the alkynes are what? sp hybridized. Of course, examples are acetylene, metacetylene, ether-acetylene. These are just the common names. These are just the common names. Now, they have a general formula CnH2n minus 2. CnH2n minus 2, where n start from 2. You see, for the double bond alkene and then the triple bond alkyne, you always will need 2 carbons to have the double bond or the triple bond between them. So n can never be 1 for an alkene. N can never be 1 for an alkyne. N can be 1 for an alkane, which is methane. So for an alkyne, n start from 2, 3, 4, 5, up to infinity. So from the formula there, if n is 2, then you're going to get what? C2, then 2 times 2 is what? 4, minus 2 is what? 2. So C2H2. If n is 3, C3H4. If n is 4, C4H6. If n is 5, C5H8. So this is the formula of the alkynes that you generate when you know the value of what? N. Can somebody give me the formula for an alkyne with n being 8, when n is 8? When n is 8.
C8H14.
C8H14, good. What about when n is 9?
C9H16.
H16.
Yes, good. C9H16, good. What about if n is 20?
C20H38.
C20H38. Lastly, what about if n is 1000?
C1000. H998.
Yes, C1000 H998. It's okay, mute yourself. Okay, mute yourself. Hey, online. First is, what did he say?
This is a
Okay, so beginning like this, it sounds so sweet in your ears, but then in the middle, then it starts sounding like hot water in your ears.
Oh,
First, this is cracking me up here. How I wish I had seen this guy. It's making me laugh. Anyway, that's just by the way. So you'll be fine. I keep on saying you'll be fine. First, you'll be fine. at the end of the semester, I know you call me and say that, Doc, I'm fine. So don't worry, okay?
Okay, Musa, Amen.
All right, so these are the formulas, and like I said earlier on, alkynes contain the triple bond that characterizes them. That is their identity. That is their unique identity. The hybridization of the carbons bearing the triple bond is sp, and there's a bond angle of 180. And anytime the structure of a compound have a bond angle of 180, then that tells you that the compound is linear. So the shape of alkynes are all linear. The alkanes are not linear, they are tetrahedral. The alkenes are not linear, but the alkynes are what? Linear. So take note of this formation. All these ones are not important. Okay, good. Now, there are two types of alkynes. We have the terminal or the internal. Okay. Now, whether it is terminal or internal, it depends on the position of the triple bond. The terminal ones, the triple bond is always at the end. The triple bond is always at the end, like this one. You could see that if you consider the two carbons bearing the triple bond, the carbon here, is it bonded to any carbon to the right? No, it's just hydrogen. So it means that the triple bond can be said to be at the end of the carbon chain. And that's why we call it what? Terminal alkyne. For the internal alkyne, if you take the two carbons bearing the triple bond, you could see that the carbon on both sides, left or right, they are bonded to other carbons. So it means that the triple bond is said to be internal, it's said to be in the middle. So they are called internal alkynes. So here, if I give you 2 or 3 alkynes and I ask you which one of them is internal, you should be able to tell. Which one of them is terminal alkyne, you should be able to what? Tell. But then the terminal alkynes are said to be what? Acidic. The internal alkynes are not. Why the terminal alkynes are acidic is because they have what we call the acidic hydrogen. The terminal hydrogen here, labeled blue. It is a hydrogen that can easily be ionized in solution. And in chemistry, when you say something is acid, its ability to produce H+ ions. So terminal alkynes, because of the terminal hydrogen, they can ionize and release the H+ ion in solution. So all terminal alkynes are acidic, but the internal alkynes are non-acidic. And I hope this is clear.
Yes, sir.
How do we name alkynes? We've touched on the nomenclature of alkenes. We've done nomenclature of alkenes. Now here we are with alkynes. How do we name alkynes? All the IUPAC rules we learned in the alkenes and alkenes, I hope you have not forgotten because they are all important here. Just that we'll be adding 1 or 2 new rules. Okay. Now, the nomenclature system for alkynes is identified to that of the alkenes, except the suffix YNE, which is used to indicate the triple bond. Okay. As in the case of alkenes, we have the ENE. So if it is a 2-carbon alkene, we call it ethene. Now, the ENE, the last 3 letters in alkyne, you replace it with YNE. So it becomes what? Ethane. If it is pentene, 5-carbon alkene, the last 3 letter ENE is replaced with what? YNE. So it becomes what? Pentane. Pentane. So take note that the last 3 letter in alkynes is always what? YNE. Okay. So in naming an alkyne, you first of all select the longest continuous carbon chain that contains the triple bond, because the triple bond is the functional group of alkynes. So if you are selecting your longest chain, it should contain the triple bond. If it does not contain the triple bond, then you are not naming an alkyne. So if I give you a carbon chain of 6 with a triple bond, then that will be what? Hexyne. 7 heptine, 8 octine, 9 non-9. So the first 20 alkanes I asked you to learn, it still holds here. Because if you know the number of the number of carbons, then it is easier to generate the parent name of the alkyne from it. So can somebody tell me an alkyne of 20 carbon, how will you call it? Alkyne of 20 carbons, how will you call it?
Icosine.
Icosine, great. Icosine. What about an alkyne of 10 carbons?
Decyne.
Decyne. All right.
Decyne.
What about an alkyne of 4 carbons?
Butyne.
Butyne. Good. You guys are good. You guys are good. You break all my papers. Don't worry.
This is the simplest way of form.
Okay, so after you've selected the longest continuous carbon chain containing the triple bond and getting the parent name, like we did for the alkenes, wherever the triple bond is, we need to number the longest chain so that we give the least position to the triple bond. So it means you check from both sides in terms of the numbering, whether you are numbering from left to right or right to left. In which one of them would the triple bond be given the least number? So that is the second rule. Okay. Then when you know the number, then that number should precede the parent name. Okay. So if it is position 2, then it becomes 2 maybe pentyne or 2 octyne or 3 hexyne, meaning that 3 is telling you the position of the triple bond in the long chain of either 6, 7, or 8 carbon. Then another rule is that when you have 2 or more of the triple bond, then you introduce the prefix a-diene. Di means 2, so diene. If there are 3, a-triene. Okay, if there are 4, tetraene. And that is that. Then all the other rules we learned in our case, they still hold. That is, if after selecting your longest chain, there is any group.
The tetraene, can you also say butaene?
Can you also say what?
The tetraene, can you also say butaene?
No, please. These are prefixes which we use di to denote 2, tri to denote 3, tetra to denote 4, penta to denote what? 5. Okay, so that's what you have to use. So I was saying that after selecting your longest chain that contains the triple bond, any other group that is not part of the longest chain, we all know it's considered what? A substituent. And the substituent must be named before the parent name. So the substituents too, you need to know their positions. After the numbering, that you are giving the least number to the triple bond, at least it will help you also to get to know the position of the substituent. Then again, if you have organic and the inorganic substituent, the inorganic substituent must be written first before the organic. Then again, if you have 2 or more of the inorganic substituent appearing, arrange them in alphabetical order. Like bromo comes before chloro. Chloro comes before iodo. Then when you have 2 or more of the organic substituent, then again, you also have to arrange them in alphabetical order. Like ether, which is start with E, comes before meter, and then eta comes before proper. So when you have two or more of the organic two, you arrange them in what? Alphabetical order. So you can see samples of structures of our kind on the screen and their names. Please kindly let us give ourselves some 3 minutes to 5 minutes, because this is naming, and naming, we always bring a lot of questions in the naming. And when a naming question comes, you shouldn't get it wrong. Okay.
Sir, please, sir.
Yes.
Please, let me ask this question. Can there be a situation, okay, what I'm seeing on the screen, where you have the triple bond and then a double bond
Yes, there
at
can
the
be that
same time?
situation. There can be that situation. That is what you rarely see on the board. Okay. Now that situation, when you have a double bond and a triple bond, note that the triple bond takes precedence over the double bond. The triple bond is superior in terms of functional group than the double bond. So you don't name it as an alkene, you name it as what? An alkyne. Just that your name should also have the double bond in it, in terms of its position in it. Okay. And that's what you have an example there. So please, let's give ourselves some few minutes to look at the structures there and then the name. When we are back, you will tell me if there are anything about the names provided that you don't understand, then I'll explain.
Hello.
Hello. Mama in big kaka. Charlie, first one, first one, he didn't, as I maintained, Hexa 1, 3, the
Say mostly na naming of compounds no. Sometimes no. Like when I maybe do some questions, most now we just start from where you get the shots. Maybe carbons near in T. I was even looking at from the right place.
1, 2, 3, 4, 5, 6.
And
You want a
6.
6?
That's a hexa. Hexa. 1, 2, 3, 4.
Okay. And hexa the other. And hexa number. Now, the even on the in 5 wine.
Maybe. Hexa 1, 3, diene 5 I. That means that hexa 1, 3. He started from the left hand side. Oh, share.
Sure.
1. Now then I will come once.
So the in 5 wine. I'm not my confusion. 1, 2, 3. Okay. So 3. Okay. 5.
So
5.
if somebody asks the question that double bonds and triple bonds at the same time, the same structure, you get that. Somebody asked that question. So you see that in a structure you have two double bonds. Okay. So 2 double bonds and then 1 triple bond.
Okay.
I'm sure that is why we are having the 1, 3 in. You get it.
Yeah, so the name is started from the right.
Yes, it seems so.
Sure.
It starts from the right. The numbering from
the first double bond, the third double bond, and the fifth one is the triple bond. That is
the triple bond. Exactly.
Hexa 1. That's the triple bond number carbon 1. So
No.
Die no die so na ama my coffee die in the
Yes,
inside
because the
one.
double bonds are
Here, no.
kings.
Let me start from the right.
Out.
Is it
Yeah.
because a double bond into a die and I said it.
Yes, and we have two
Hey,
of them.
Double bond.
The
Double.
E signifies our king, the double bonds, and because there are two, that's why you see the die.
You have to die.
Five. So I don't know.
No. It's 1-3.
The you one hexa one correct. Then 3-5 die in one.
No.
5 because say we counting from the right side now. Who say the triple bond is on the carbon on the 5th carbon. Anything 5 iron.
The triple bond is never on the 5th, it's on the 1st.
The triple
No, you start from right. Right.
So the one saying say to start from the left now. Any over from the left, tell one. And so can never say. On starting from the left because there's a triple bond on the left. But what are one thing
Shadow. What was it? Showing itself hexa one eye. Let's say we'll give you preference. Triple bond.
No. The hexa is talking about the number of carbons, not the.
And yeah, hexa.
The number of carbons.
Hexa is 6. Very good.
You
But
see,
the triple bond is on carbon number 1. We have hexa 1.
This
the hexa over
we
there.
started from the right. They started from the right.
They started from the right. Also, you are naming from the alkene, the double bond compounds, double bond into 1-3 and starting for alkene.
Hello. The 1 and 3 are for the double bonds. They are showing the position of the double bond.
The double bond,
not the triple bond.
That in
Oh, na me almost 3 na robo 5 na ko 3-5. Was ni omuni na double bond. So na ko 3 dan in 5-1. What na men jadi?
Yo, guys. So
I don't know who is speaking about. The hexa can be brought to the last part of the naming.
And no problem.
Yeah,
no
that's
problem.
my problem.
And no problem. The one. Ufa hanso obidu James is anete. So between the view to between the can. As me who na me san things you wanna.
Yo,
yeah. So double bond,
guys,
from 1. Now 2, 3.
Guys, yes, first one, another one now.
Hello. Let's look at this. Let's start from the right. When we start from the right, we have 1 carbon over there. So at the end of every joint, we have a carbon over there. So starting from the right, you see a carbon over there, and that carbon starts with a double bond. That's carbon double bond. And that is 1 is coming. Now, if you move from there, the second one double bond. That's where the
hexa 1.
So then you have the hexa is the number of carbon in this. How do you call it? This hydrocarbon.
The chain.
Is the number of carbon over there. That's the hexa. That's 6. Now, here the ion is the alkyl group. That is where the triple bond. That's the R. Now, if you look at this, we have how many double bonds? We have 2 double bonds. and we need to name those three double bonds before the last alkyl group, which is starting from the fifth carbon when you start from the right.
Hello. Yeah. Okay. So. Hello.
Lucky enough. Your name.
Hello.
Please, sir is back. Oh, Doc is back.
Interesting.
All right. So I was trying to mute those who are having background noise. All right. So I think there's been some engagement among yourselves, and you have looked at it. Please, I will not leave it open for everybody to talk, lest there wouldn't be any form of orderliness. So at this stage, if you have any concern to any of the structures there in the name, if they are all okay and understandable, then we move on. You can put up your hand.
Sir, please, the slide is awful.
Which slide is off?
It's not showing on the screen.
Your screen.
Your slide.
I have seen Azuma Peter and then Eliasu Yakubu. So I'll take one after that. Azuma Peter.
Okay, thank you, Doc. But first of all, the slides, they are no more appearing on the screen. So we are just seeing only your profile pic. Okay, now it has come. Thank you.
You have to check your machine, yes.
Okay, what I want to ask is that looking at the first one, it has disappeared.
Okay. Are you using your mobile phone or a laptop?
Listen, I'm using mobile phone.
So that is the reason. The slide is still showing.
Okay,
it has disappeared.
I'll get back. Sorry, sir.
It's still showing, even though I'm using mobile
It has
phone.
disappeared.
So, yeah, you're setting.
It has not disappeared. It's still there.
Yeah, we cannot see it.
Oh, what phone are you using?
We cannot see you.
Mine is still there.
Mine is still there.
The neck, because the majority are saying that
the majority of us cannot see it.
Please, my slide is showing. If you cannot see, go back and check your own setting, your phone settings. That is it. Don't disturb.
Please tap on the profile picture of the presenter.
Still, when you tap on it, it's not showing.
It's still not coming.
Double tap. Double tap.
This time around.
We've been doing that and stuff.
Please rejoin. Rejoin.
But the slide is still there. It's still there.
So you'll be using the slide. It cannot be found. The slide is there, and then time is going.
The slide is still there.
Eliasu Yakubu, if you can't see the slide, then don't put up your hand for me to call you. Yes, Ruth Aqua.
Sir, hello.
Yes.
Okay, sir. I just want to ask some
no,
question
you
about
can't ask because I've not seen your hand up. JD, you can't ask any question. Eliasu Yakubu.
I'm sorry, sir.
Okay, hello, sir.
Yes, go
this
ahead.
Is me. Please, can I talk?
Yes.
All right. With the first one, I think I'm having a confusion. Does it mean in naming such a compound, you have to start with the alkenes before the alkynes?
Yes, for the first part.
Okay.
Yes, for the first part of the question. So what we are saying is that, like I indicated, the alkynes are superior than the alkenes. But then the alkenes too are also a functional group, so you cannot ignore them in your naming. So you start your naming as if you are naming an alkene. We already know how to name alkene.
Yes, please.
So you start the naming as if you are naming an alkene. But because there's an alkyne functional group, you end with what? The ine.
Okay.
Yes.
All right, sir.
Any other?
Please, you cannot still see the thing. Oh. I don't know. I rejoined, but I'm not still seeing it.
Yeah,
So
we can see.
Please,
we can see.
please, kindly take this for me. The slide is on, and we don't want to use the rest of the time of I can't see. In fact, that will disturb us. We will be standing at one point. Please, if you can't see, deal with your machine and get it rectified. Please don't interrupt.
Okay, sir.
Yes.
Hello,
sir.
Sir.
Go ahead and ask your question.
My question is, looking at the first diagram, so are we going to number it
It
from
is
left
not.
to right?
It is not a diagram.
Right to
We are
left?
not doing visual art here. It's not a diagram. It is a structure.
Okay, the structure. Okay, looking at the structure. Sorry. Are we going to number it from left to right or right to left?
Good. That's a good question. So you number from right to left. Okay. Now, what I'm saying is a good question is that IUPAC is saying that if you are naming an alkyne, make sure you number and give the list number to the triple bond. In this instance, you have a double bond and a triple bond all there. Now, check the numbering from left to right. You could see that the alkyne will be 1, isn't it?
Yes.
Then the 2 double bonds, what will be the position? The first one will be what? 3. Right?
3, sure.
And then the second one will be what? 5.
5. Yes.
Good. So now pay attention to this numbering. So 1, 3, 5. 1 for the triple bond, 3 for the double bond. Then go to the right and also start numbering. The first double bond will be what? 1, isn't it?
Sure.
The second one will be what? 3.
Yes.
And then the triple bond will be what?
It will be 5.
Good.
Okay.
Now, IUPAC is saying that this is a special case. When you have a compound having a double bond and a triple bond, okay, and irrespective of the direction you are numbering from, you are getting the same numbering system like we see here. When you go this way, it's 135, over here is 135, okay?
Okay,
IUPAC is saying that in a situation like this, even though the compound is an alkyne, please give the list numbers to the double bond, but still name the compound as an alkyne.
All right.
So the reason why we gave the 5, which is a higher number to the triple bond, is because we are getting the same numbering system, 135, 135, irrespective of the direction you are going. And so in a situation like this, we will give the list numbers or the list position to the double bond, but we will still name the compound as an alkyne.
Okay, thank you, sir.
Good. Any other question on the structures there? Yes, Patience. Wahima.
Thank you, sir. But the structure, the first structure, I can see that the naming of the carbon chain started with the carbon chain. That's the hexane. Begins the naming. I don't understand that.
Okay, so you could have also written it as 1, 3 hexadiene, but then the last letter E will not come, 5 ine. Okay. So I have written it. I brought the numbers in the middle.
Yes.
But you can also begin the numbers. Before. So
that was what I was thinking.
Yes, 1, 3 hexadiene, but then the E will not come, then 5 ine.
Okay.
So
Thank
that
you.
is also right. They are all accepted.
Okay.
Any other question?
Please, yes, sir.
Okay, go ahead.
when you look at the second structure, that is cyclohexane.
Yes.
Cyclo is a ring structure. It indicates a
Yes.
ring structure. And when you look at a ring structure, we have 6 carbon ring.
Yes.
You know the structure very well. That's why we get a hex over there. But
yes,
the N indicates a triple bond. So
yes,
when naming this structure, it doesn't. You don't normally look at the location of the M. That's why we didn't indicate the number over there.
Okay, that's a good question. So for cyclohexane, okay, irrespective of where the triple bond is in the ring, it is going to be 1 always. 1 cyclohexane, 1 always. It is important for us to bring the number when we have other substituent groups. But in this form, where there are no substituent, somebody say it's not so much important to bring the position 1. But assuming we put some substituent group on the ring, where the substituent will have their own position, it's also important that you indicate the position of the triple bond in the ring.
Okay.
All right. Yes, any other? So let me do this. I'm going to stop sharing my slide and share again, and let me see whether those who are complaining, they will see it again, because a number of you can see my slide and you are speaking to it. But for the others who are complaining, let me stop sharing. I'll share again, and let's see whether that can resolve their issue.
It's not showing. You can
I can see it now.
showing now.
Thank you.
It's now showing.
Don't say it is now showing. It was initially also showing.
It's not showing to all of us.
So we can see it now. That's how we have to put it. We can see it now.
Okay. All right.
Okay, we can see it now.
So if you can also ask your question, ask, and now you can see it.
So please, go over the explanation again.
Please, which one? They ask specific. The first one, which one was the first one?
The one you were explaining when our screens were off.
Hexa 1 3
Hello, sir.
Yes.
Please, can I give a brief explanation about the first one? That's my colleagues are talking about.
Yeah, go ahead. Then I'll come in.
Okay. Concerning the structure over there, someone asked about, is it suitable for us to always go about naming first the alkene? Me, to my own opinion of to my own research, I think that's the most suitable way, because when you look at the structure, the first thing that will come to your mind is how the carbons have been joined. And when you read about and you look at the carbon very well, and you try to normalize 1, 2, 3, 4, 5, 6. And normally, it's a string chain. That means you're talking about alkene over here. That's hexane. And per me, I normally go with naming the structure from the right hand side, because we want the shortest possible way to find most of the the naming over here. So when you look at the first, when naming from the right, look at the first chain. You have a double bond over here, and the second one, the first chain 1, there's a double bond 2. On the third chain 2, there's a double bond over here, meaning you are talking about in alkene over here. So it's 1, 3. Since it's 2 double alkene, it's di. So 1, 3 diene. You write that over there. From the third chain, from the third carbon, 4th carbon, you could see there's a triple bond over there. And when you talk about triple, we are talking about alkyne over here. And it is on the 5th carbon. So that means it's 5 iron. So that's the simplest way to me we can go about it, rather than starting from the numbers 1, 3 hexa. If you don't take it, it might confuse you.
That is a crude way of also understanding. If you go by your understanding,
hello, sir.
In a different system, it might not work for you.
Okay.
Hello, sir.
Yes.
Sir, please, so I thought initially you said that now with the double bond arcing, you start the naming, you start with where the double bond is. If it is alkyne, you equally start with where the triple bond is.
It's closer,
That is,
yes.
that one will even pre-inform. And looking at what is here, looking at it, you have 6 carbon, that is hexane, or in the triple bond it will be hexane. Okay, let's say it is hex. Then the triple bond is on the first carbon. Is that not the case? But it seems my colleagues want to start with the, I don't know, they want to start with the double bond instead. And that's making me confused the more.
Festus, it seems to me that you are the one who is not being confused. You are rather even following things up, okay? So don't see yourself as confused.
Okay.
Yes, you are right. We are following a certain rule. Is that right? And the rule is that when we're naming our kings and we are looking at which directions to start numbering from, the rule says that number from the direction that will give the lowest number to the double bond. Now, when we're starting with the alkynes, the rule says that number the chain so that you give the least number to the triple bond. Okay, so with the same concept, you would have wished that this one we number from left so that the triple bond, because we are naming it as an alkyne, so that the triple bond will be 1 instead of the 5. Is that right? But that is where
Yes, sir.
I'm saying that anytime that there's a triple bond, always number from the direction that the triple bond will get the least number. But the compound that you see there, there's a special case over there. The special case is that when you number from the left, as you want to do, the position of the double bond and the triple bond will be 1, 3, 5. Then when you number from the right to the left too, it's also going to be what? 1, 3, 5. This is a special case. So where you are getting the same numbering system from both sides, IUPAC is saying that, oh, when you are confronted with something like this, then please give the lowest number to the double bond, even though you are going to name the compound as an alkyne. So it's just a special instance. But apart from that, always make sure that the triple bond is given the least number. But this is a special case where we're getting the same numbering system. So if I'm to summarize, if you have a triple bond without a double bond, always number so that the triple bond is given the least number. If you have a triple bond and then a double bond, still the idea is that the triple bond should be given the least number. It is only when both sides of the numbering is giving you the same numbers, then IUPAC is saying that in that situation, give the least number to the double bond, but still name the compound as an alkyne. I don't know whether this makes it clear.
Yeah, very loud double.
Good.
Sure.
So this is just a special case. I'm trying to see if I can use my chem draw to give you another example. Let me try and see. So you hold on for me. Let me see whether that will work. I want to open my chem draw and see. Okay. So please permit me to stop sharing this slide, okay? Let us all go to the chem draw where I draw all these structures from, okay? And then let me see whether I can do something there to help you understand. So let me see if I can share my chem draw page. Can you see my chem draw page?
Yes, please.
Good.
No.
So, no?
Yes, please.
So please, we can see it.
Very good.
I can see it actually.
Good.
Yes, I can see too.
So you can see I'm drawing some structures.
Yes, sir. Yes, sir.
Good.
Wait,
So
yes.
that's how I'll show you later. The chemistry major people, I'll show you how to draw this. I'll give you this program, and then I'll show you. So how many carbons can you see?
Says 7. 7.
So if
Seven.
it's an alkane, in an alkane, so you call it what?
Heptane.
Hey, heptane. Good. Good.
Yes, heptane.
Now watch something. I am introducing a double bond, okay? Have you seen it?
Yes.
Yes, sir.
Good.
Yes.
So how will you call this one?
Now, 13. It's in the king.
How will you call it?
Heptane. 1 heptane.
Heptane.
1 heptane.
Hept
Yes.
1 I. Heptene. Hept
It's
1
not iron.
in.
It's only double bond.
Hept 1 in.
One
Yes,
heptene.
heptene.
One
One
heptane or
heptene or
hep1.
one heptene.
One
One
heptene.
All right. Hold on.
There's nothing between Bayern Munich, Bayer Leverkusen, so now the same kind of is like a different class. Travel, family, any of that. Interestingly, I looked at game an exciting fixture. I looked at both these games with passionate information Leverkusen. Until previous
Okay. Can you see the name?
I think you have the one thing. I'm not sure.
Yes,
One aim.
Yes, sir.
All right. Please, those who have audios at your background, don't omit yourself. You are telling us that you are doing two things at a time. So stop disturbing us. And then let's follow because we are doing something important here.
Yes, please.
Good. So let me then go ahead. Now there's a double bond there. I also want to introduce a triple bond, okay? Are the two there the same? The structures?
yes, sir.
Yeah. Yes, they are the same.
Yes, yes.
Yes,
Good.
yes. Yes, sir.
Oh, who is that? Please, are the two the same?
No.
sir.
No, sir.
No.
Very good.
So now
No, sir.
the straight chain is still 7, and then we have one double bond, one triple bond. Just that the positions are
different.
Good.
Yeah.
So let me just let you see the name for the second one. Please forget about the E. You know why the E is there? The E is the geometry of the double bond, okay? Antigen, okay? But then you forget about the E. The E is not an important, thing here. Look at the rest. Hept 4 in what? 1 I. Is that right? Is that right?
Yes, please.
Which you can write the same as what? 4 heptene 1 I. Is the same thing. Now, based on this name, where was the numbering started from? Was it left or right?
From left. Right. From left. From left.
From the left.
Yes.
From left.
From the left.
Why was it from the left? It was from the left because the compound is an alkyne, isn't it?
Yes.
Yes, it is.
Yeah.
So we are supposed to give the triple bond the least number.
Sure.
If you go and start from the right, the triple bond is going to be what? 6. But if you start from the left, it is 1.
Yes.
So here, the focus is not on the double bond, it's on the triple bond. And it's because if I start from the left, the number of the triple bond is 1, the double bond is 4. So please, we have what? 1 and what? 4. Is that right?
Yes.
Now, when I start from right, the double bond is what? 3.
3.
And then the triple bond is what? 6. Can you see?
Yes.
Now, the 1, 4 from left to right, and then the 3, 6 from right to left. The numbers there, the 1, 4, and 3, 6, are they the same?
No.
No.
They're not the same. So it means that because they are not the same, you have to go and give the least number to the triple bond because they are not the same. Now, let's come to the first one. Let's come to the first one. When you go from left to right, the triple bond is 1, isn't it?
Yeah.
And then the double bond will be what? 6.
6.
Then start from right. The double bond will be what? 1.
1.
The triple bond will be what? 6. So you see, you are getting the same numbering system: 1, 6, 1, 6.
Yes.
Yes.
This particular situation is what IUPAC is saying that it's a special case. So in a special case like this, even though the compound is an alkyne, number from right so that you give the least number to the double bond, even though you are naming it as an alkyne.
Okay.
Because they are having the same numbering system on both directions. IUPAC is saying that, oh, it's an alkyne. The triple bond should have been given the least number. But because of this special numbering system, 1, 6, 1, 6, give the 1 to the double bond and name it as an alkyne. Now, I want us to see. So, if you are to do that, what will be the name?
Please, sir, you don't get you.
Now, look at the name.
6, 9.
Look at the name. Which is the same as 1, 13, 6, 9. So you could see that in this name, it is still a kind that we have named it. But then we give the least number to the double bond and not a triple bond, which is not the normal rule. And the reason is because of the same numbering system we got, 1616. That is why IPAC is saying that when you have this same numbering system, please give the list number to the double bond, but still name the compound as an alkyne. That one is different from down here. For the down here, we got 1, 4, and 3, 6. So the numbering system are not the same. Then always give the list number to the triple bond.
That's the normal rule.
Yes, that's the normal rule. Always, when you see an alkyne, a triple bond, and there's a double bond, just forget about the double bond, and then triple bond should be given the list number. But that is because if you number from both sides, you are not getting the same numbering system. But as soon as you get the same numbering system, then the rule changes, and we give the list number to the double bond, but still name it as an alkyne. Please, I hope this is clear.
Hello, sir.
Yes.
Sir.
Yes.
That means that in a structure you have double bond and triple bond, you have to give the name to the triple bond.
Always, because I've told you that, you see, we started from alkane, single bond. Then we came to alkene, double bond. Now we are at alkyne. So it's like we are moving in order for superiority. So if there's a double bond and a single bond, you don't name it as an alkane. You name it as an alkene. If there's a double bond and a triple bond, you don't name it as an alkene. You name it as what? An alkene. Hey, I say more.
Thank you very much, sir.
In fact, I will end the class here. It's past 11.
Question.
No, I can't take any question. Okay, Esther, go ahead.
Yes, one. Sir, please, why do you say that the compound has 6 long carbon chain? Sorry, 7 long carbon chain, because I can see 6.
Oh, let me help you count. Okay, Esther, let me help you count. Let me go back. All right. Coming. Okay, so do you see my cursor?
I do.
Okay, what it is 1. The end here is 1.
Yes.
Then this place is 2. Down here is 3. Over here is 4, 5,
Right.
6. Then it ends with 7. So you see, they are all lines. We call this one the dot line structures. Beginning of a line is a carbon. Where that line ends is a carbon. Okay. Beginning of the line is a carbon. Where the line ends is a carbon. Then it joins another one. Where it joins is another carbon. So wherever there's a join, there's a carbon there.
Okay.
Esther, are you okay?
I'm okay.
So Imas will say the edges.
The edges. Okay.
Okay, so that means we're not necessarily counting the lines.
Oh, nah.
No, it's not the line. The line represents a bond. But then the edges, the beginning and then the end of the line, they represent carbons.
Okay, I'm fine. Thank you.
Great. I'm happy you are fine. All right. So it's past time, and do you have another class now?
Physics is loaded.
So we have biology. We have biology at 12.
Oh, okay. So we can continue. But then the point is this: we should have finished our kinds today. So, please, on your page, okay, before next week, can we fix 1 hour somewhere in the course of the week and do a makeup lecture? Please, I will leave you to discuss and then communicate the day and the time with me, because I need to finish our kinds. I was going to the synthesis and then the reactions of our kinds. That is what is left. This one, when we get 1 hour, I should be able to finish so that next week we will be left with the last topic, which is the aromatic hydrocarbons.
Please, Monday we are on midterms, so we can do it. Monday, God willing, we are on midterms. We are not going to school.
Yes.
Yeah, so
But we'll be
please,
sending our kids to school, but the time should be.
so please, pick a time on that day that it will suit most of you.
From 4:30.
Definitely, even our normal meeting times, not everybody come for lectures. So nobody should tell me that everybody will be present. But at least a time on that day, I think if it goes to
Sunday,
the evening, it will be very good for me.
It's from 4:30 to 8.
Okay, then sir, can you please share the rest of the slides, like the last topic too?
Yeah, definitely. That's what I do. You know, the kinds I shared them last week. So after today's lecture, I'm going to share the aromatic lectures.
Yes, that will be.
And then the rest will be.
Can you use super aromatic?
Yeah, we have to go and print it so that we
Sir,
can.
please. Thank you. On Monday in the evening, we'll be having curriculum studies. So I'll suggest we do it during the daytime.
He said we should come together and think about it.
That will be from 7 to 9, please. 7 to 9 p.m.
So hours can be before that time.
Okay.
Monday 4:30. 4:30 to 8 5:30. Some of them will say 7. 7 they are maybe just 1 hour.
I think we can do it in the morning.
Monday will be
Monday.
Please, let's discuss it in the group. What's up? That one will be better.
Okay. I have another lesson now, so maybe I'll leave you. Bye for now.
Okay. Thank you.
All right. Thank you.
All of you should meet me at the group. All of you.
Meet you where?
At the general group, the chemistry one.
What of the That's the perfect place for us to plan. So let's do it and leave.
And please, some of us are not on the platform.
Okay.
You can send them hi.
I suggest Sunday evening, 7 to 8, right? 7 to 8, right?
Yeah, 7 to 8, we have lesson there.
Sunday.
Sunday.
Possibly.
Physics, chemistry, don't we have a lesson on Sunday?
I think physics have a class on Sunday.
Yes, we have class on Sunday. We have two, morning and evening.
I suggest Monday, so the Monday will be.
The Monday is okay. Let's fix it on Monday.
The Monday,
With the Monday, the lecturer himself. He might not be available during the day, so it should be in the evening.
Yeah, I think in the evening, 4 o'clock is okay.
I think that the curriculum studies has been scheduled in something.
Yeah, it has been scheduled to Friday.
Monday. So Monday is.
It's on Wednesday.
The evening is okay. Monday evening.
It's Monday. Let's suggest around 4.
Okay, but if
that is the form, if only he will be available.
I think Monday.
But if
so
we are using
maybe
the
the class, the course rep should contact him with the time and then get us feedback.
Let's give him 4 o'clock.
Chemistry major for now more. Chemistry, so and those doing the major.
Those of you who are saying you have physics classes, is it physics minor?
No,
we have physics major. We don't have physics minor.
Hey, now physics major, are you?
Please contact your group and then find out, please. Yes, biology major, chemistry minor. So
Monday the time was 9, 7 to 9. Oh, bother. 7 to 9. Oh, bother.
I think we have biology
Biology from 11:30 to 2:50.
I think 12. 12 to 4.
Okay.
Yeah.
Okay, thank you.
Me pa trouble for obi wo a owo Techiman Center or Mammy who I Techiman or Center or Techimaya. I was one for DMMA.
Mpacho, me so me was Sunyani City Center, but me who's Sunyani for?
Na time bene de ashe. Obi e free so.
Please, I think we suggested Monday 4 o'clock.
Monday 4 o'clock.
Yes, please.
Okay, thanks very much.
Mpacho, what is Sunyani? Mariana.
Mary.
Okay. Apart from Mary, who again?
Patience to
And
know.
Techman for one case na critical. Techman for no Techman Center. What?
I say move.